Hello?
Yes, sir.
Yes. Hello? Is it fine?
Yes,
So
yes.
small
Hello?
sentences are quite. So you are audible, but voice is breaking sometimes.
Breaking.
So yeah.
Let me check. Hello?
Yeah.
Yes, sir. You are
Yes,
clear
it's
now.
loud and clear now.
Sharing the screen. Hello?
Yes, you are loud.
Hello?
Yes,
You are loud, sir. Now.
Yes,
Yes,
Yeah.
coming
yes, sir.
loud and clear.
Your screen is visible.
it's
Okay.
visible.
So today's talk is the multi-robotic system. So it's one of the key research domain in the field of robotics. So basically, I'm looking into the consensus and coordination part of this multi-robotic system domain. So it's a broad area. So there are lots of sub-domains in the field of multi-robotic systems. So basically, in multi-robotic system, we are deploying using multiple robots for accomplishing. So the multi-robotic system is basically multi-agent system. So while talking about multi-robotic system, we need to start with multi-agent system. So this concept of this multi-agent system has been derived from biological systems. So the researches of the first of this kind has been done by biologists, especially this is very common in nature, biological systems. And you can see in the screen, this slide, the V formation flight of birds. So it's that's very common. So Steve Ogle, a famous biologist, so he has done an experimentation in this birds. He has implanted some heart monitors in white pelicans, and he has some interesting observations. And he found that the birds, there are some energy benefits, and they are flying for some aerodynamic benefits. And apart from that, the interesting observation out of his research was that so this individual decisions taken by each bird in a V-shaped formation through local interactions is finally coming out of the global behavior. So this is one of the, this actually researchers try to explore this concept and they try to extend this concept from natural systems to artificial systems. And this has paved the way for the emergence of this area of research called multi-agent. So where we have multi-agents and we can delegate the mission part as a task also we can delegate multiple agents. So and we can complete the task more efficiently with the multi-agent system rather than a single agent in for many applications. There are many applications for this particular domain. So I'm coming to that. So we're looking into biological systems. So we can see, especially in birds, and especially in birds and many biological systems. These are some of the common swarming behaviors you observe in the system. Outjoining, path following, collision avoidance, obstacle avoidance. This actual researchers try to explore this concept, and we can this has been extended to artificial systems. And again, we can delegate this intelligence also among multiple agents and do many tasks more efficiently. Multiple agents. Multi-agent system can do things more efficiently than an intelligent system. So basically, I'm looking into the cooperative control part of this multi-agent system. So our agent is a robot here. So we have multiple robots being deployed for completing this. So the applications of this multi-agent system is from even in power systems and microgrids to even satellite space systems and satellites And there are many applications we can use. Distributed computing also is asset management, and many applications are there for this multi-agent. Wherever we are actually delegating the multiple nodes, so we can use this concept. So here we are, our agents are mobile agents, so we are having mobile robots. So we are delegating the power, delegating the task, and again, so we have said why the robot formation, why we need it, why we need multiple robots. So there are some from the figures, it's clear. Some of the applications is multi-robotic system. There actually this multi-robot system can perform better than a single platform. So the advantages are mission efficiency in terms of time and quality, flexibility, adaptability, of course, accuracy and energy efficiency is also more for that. Some tasks actually difficult for a single agent to do. So those steps, especially we deploy multiple agents. We are robot. Application. So we can deploy this multiple robots to accomplish this task. So civilian applications. Civilian applications include surveillance, search and security. So in platform, rather than a single platform, multi-agent system, multiple platforms can do better in terms of the area of coverage or the data, higher resolution data extraction, and all this point of view, a multiple platform or multiple nodes can perform better than single platform. So civilian applications include pipeline and powerline control. This was one of the work that was worked on also. So the pipeline in long distance pipelines in desert lands, there are oil and gas pipelines. It's quite difficult for a human to go and inspect for a fault or something happens. So in such cases, even a single robot is quite difficult. So we can deploy multiple robots for this patrolling, the live patrolling of oil and gas pipelines and farm aerial spraying. It's one of the applications. This is some of the applications where actually this multiple robots have already been deployed successfully. So this farm aerial spraying, if you look into that, so for this very big farmlands, we can deploy multiple aerial robots for disease detection and pesticide spraying and all the things. Survey also. So rather than a single platform, multiple robots can perform better, more efficiently, and in terms of time and quality, it will be good performance. And forest fire suppression, then cooperative transportation, that is even visible in this figure. So robots can transport things and handle things also more efficient. So here another figure, you can see the risk operation, how the aerial robots are employed for the risk operations. And
Sir, sorry to interrupt you.
Yeah.
Your voice is breaking. So can you near
Hello?
you or away from you?
Hello?
No, sir, not audible.
That we will check.
Hello? Hello?
Not audible.
Am I audible?
No, sir.
Hello? Hello?
Yes, sir.
Hello? Hello?
Huh.
Audible?
Yes, sir.
This is
Now
very
audible.
yes. Now audible.
Okay. So these are some of the applications again. The same thing which I've discussed: search and risk operations, surveillance, remote sensing operation, localization. So this is all are the applications that are system which are deployed implemented. In satellite formations, we can stop a single bulky platform. We can deploy multiple micro satellites. So this way we can reduce the launch cost, and even we can get high resolution data. High resolution data extract is one of the major advantage of deploying multiple satellites instead of a single bulky platform, because of in terms of wide area of coverage and meteorological and environmental applications. It has been used rendo and docking operations. So rendo docking means one spacecraft is following other spacecraft and mechanically getting coupled, especially for International Space Station maintenance and all. Already these things being done. Mapping, high resolution interferometry, and all the things. So these multiple platforms are already been deployed. Multi-satellites have been deployed. So here I told you already this multi-robot system domain is a broad area. So there are lots of sub areas in this particular domain, and lots of research has happened. Last 10 years, we can see a number of papers in reputed journals in this particular area, and lots of applications also. So, but for my area of research is currently in the control part. In the cognition part, the control of multi-robotic systems. So I'm not looking at mechanical design or hardware design. So we are trying to develop intelligence. So basically the hardware design, most of the agents have the hardware design is not the main core research domain in this one. Cognition part is more important in this case. So if you ask, just like other robotic systems, so multi-robotic system also, the main modules are perception, cognition, activation. Perception means the sensing part. So of course it's very important. Perception is very important. So advanced sensors and all, and the design of the sensors and all the things, the navigation algorithms, all the things will come to the perception model. The next is the cognition part. So where we are, the cognition part, actually we are looking at the path planning and control of the multi-robotic system. So computation, communication modules. So this all comes in the cognition part. So this we are currently looking at cognition. So actuation is actuation we know that. So I'm mainly constant cognition. This in a multi-robotic system. So these are the basic objectives. So if you just look, if you start working in the control, multi-robot formation control. So these are some of the major objectives. So I tried to cover most of these objectives, formation objectives. Mainly, we have multiple robots being deployed for completing a task. So we need the maintenance of the formation. So formation maintenance is one of the important thing. Second thing is formation reconfiguration. Of course, it is needed. The formation need to be reconfigured sometime. Multiple robots are there. It's making a shape. It is retaining a shape. So it may have to reconfigure sometimes depending upon the environmental, depending on environment. Especially the cluttered environment, it is working. Of course, it has to reconfigure sometimes to complete the task. So trajectory following, of course, if the multiple agents are there, so and sometimes actually there's a leader follower approach is very common. So in that case, trajectory following is very common. So there are n number of agents, one leader, and the rest of the followers have to track this leader. Or sometimes the agents as a whole, I mean, just like behavior-like approach. In that case, actually, multiple robots will try to mimic different farming behaviors. So in that case, it is delegated. So next is the obstacle avoidance. So of course, the agents has to avoid obstacles. It can be decentralized or centralized. The formation as a whole can avoid obstacle, or as individually the obstacle avoidance can be deployed, can be implemented. Then next is actuator sensor fault detection isolation. That is one of the key research area. Hello? Actuator sensor fault detection. Yeah. Fault detection is one of the major research domain and the research domain in this area, in this particular area. So it can be actuator fault or sensor fault, because of course, when we are deploying multiple agents, faults can happen. So detection of this thing at right time and isolating these things, and even fault tolerant controls and fault tolerant methods are very important in this particular domain. And of course, actual isolation is possible because we have multiple platforms. Even if actually the one platform is getting faulty, we can isolate it and we can it's based formation. So basically, we have multiple agents. So these agents are communicating with each other. So their end one-to-one communication becomes more complex. So of course, if we can make the system to follow a graph, so I'm talking the communication graph. So we can always ensure an optimal communication between agents. So we can accomplish the task with optimal communication using a graph-based approach. So communication consists-based formation, that is looking at this type of graph-based approach. And next is network resilience. So of course, the agents may be communicating through local network, or sometimes it may be communicating through cyberspace, and or to internet or something. So in that case, actually, the network faults can also happen. So the system should be resilient to the network faults also, like this packet loss, delays. So all these things also can happen. So this is one of the research area in this particular domain. So resilient control, network resilient control of the multi-agent system. So these are the major research domains in this particular field. And now mostly the agents are similar platforms we deployed and can be similar also. But apart from that, a multi-agent system, the main scope for this research is in this cognition part and developing the multi-agent algorithms. So when you come to this control part, so when you look in the control portion, so this is the basic control loop. I don't know how many of the people of your this is basically control loop for controlling an agent. So ith agent, we'll say. So there are a number of agents. So ith agent, we are looking to that. So we have this control module to control. For a mobile agent, we need to control the position or the velocity. And that's the control module is taking care of that. So for controlling a particular parameter of the system, so we need this sensor data. So we need to sense the position, current position, velocity, or the measurements are needed. So that is taken care by the navigation module. And even sometimes some things are not directly measurable. Some things, because sensors may not be available for some type of parameters. So in that case, we need an algorithm to estimate the things from the available measurements. So that is taken care by the navigation module. All the sensing portion, all the filtering algorithms, filter algorithms, or the estimation algorithms, all these things comes in navigation module. And next is the guidance module. So control means we need to control, suppose for a mobile robot, we need to control the position of the robot or the position of the robot at every instant to follow a particular trajectory. So in that case, we have a reference trajectory for our parameter position. So that reference trajectory, so our control module is making the robot to follow that reference trajectory or desired trajectory. So that's a function of control module. So this reference trajectory is generated by the guidance module. So that's the function of guidance part. So the guidance module is also while we are designing the reference trajectory, it should be optimal. So there are many methods are available for designing the reference trajectory. So when a robot is moving from a point A to point B, so it can take different paths. So, but all the paths may not be optimal in terms of the energy. So we can find an optimal path. So depending upon our objective, so we can design the reference trajectory for the parameter. It depends upon the parameter which we are trying to control. So in design part, when you're controlling, it depends upon the objective, mission, and the type of the agents. So the parameter control to be controlled also varies. So depending upon that, we can design the guidance reference trajectory. And from the reference trajectory, the control part will make the system's actual parameters follow the reference trajectory for the ith agents. And of course, the ith agent mobility, the control of the ith agent coming from the ith agent also, because the multi-agent system, it's a cooperative control. We have multiple agents that have been deployed. So the position control of one agent depends upon the positions of other agents also. Not only position, all the what are the other parameters of the other agents also. So of course, communication between these agents are also required, but not one-to-one communication maybe. So communication module is one of the, and there is another important module in this system. So these are the basic modules in this cognition part. So guidance, control, communication, navigation. So and the computational aspects will comes in all these modules. So computation efficiency is very important, for all these modules. So I'm basically looking at the control module, the control part of this multi-agent system. So while talking about multi-agent system, so I need to just brief this three terminologies. So these are basic architectures in formation control. We are having multiple robots being deployed for certain application. So these are the basic three architectures. One is leader follower based approach. So in this case, one of this robot is been assigned as a leader, and the rest of the agents follow the leader. And once they're in formation, they follow the dynamics of the leader with a particular offset. For a mobile robot, they will follow the leader with a particular offset. So second case is a behavior-based approach. So behavior-based approach means the agents as a whole will try to mimic different swarming behaviors. As we have seen the first slide that I've shown, the swarming behaviors like path following, flock joining, collision avoidance, obstacle avoidance, and these are some of the swarming behaviors. So in behavior-based approach, the agent, it is completely decentralized. So the control input to each agent is the weighted average of the different swarming behaviors. So it is not only following one behavior, but multiple behaviors can be incorporated in the behavior-based approach. So there is no leader assignment in this case. So all have equal weightage. So third one is a virtual leader-based approach. So in this case, there is no physical leader, but there's a virtual leader. So formation as a whole, suppose the formation we need to retain a shape, a geometric shape. So a particular point in this geometry, in the formation, geometry been assigned as the leader. So a virtual leader. So the formation as a whole act as a rigid structure in this case. And we are designing this desired trajectory with respect to the virtual leader, that point in this structure, and the virtual structure. So the main multi-robot control, if you look in the multi-robot formation control, the major research challenges include, of course, resource optimality. We have multiple agents are here. So resource optimality is one of the major, designing a cognition module with optimal resources. So in terms of the communication part as well as sensing. So optimal communication requirements, limited sensing requirements, and adaptivity to changing operating conditions. So of course, the operating conditions may changes. Whatever we design, so we are not sure of the operating conditions, the environment factors and all. So these all things, so system should be adaptive to changing conditions, environmental conditions, and of course, and system variations also. And again, to make model uncertainties. So this because mostly we are looking to the model-based controls. We can control a system. There are many algorithms are available currently. So people are nowadays using model-free algorithms also, like heuristic algorithm, neural network, or fuzzy-based algorithms are also available. So in that case, actually, model is not needed. So model-free control algorithms can be designed and implemented. But the thing which I'm going to talk about is our model-based approaches. So we are trying to mathematically model the system, and our design control logic is based on the designed model. So the model should be perfect. If you want to implement a model-based algorithm, so of course the accuracy of this one depends upon the efficacy of this algorithm depends upon the accuracy of this model. So that's very important to that. So next is a fast convergence. Of course, when we are doing the complex manuals, the system should be fast enough. The system should be fast enough. Fast convergence, convergence is very important for that in the multi-robot system. So next is resilience, fault tolerance. Resilience means fault tolerance in like network faults, actuator or sensor faults. System should be able to cope up with that. And apart from this, these are system faults, the actuator sensor faults. The next is network faults can also happen, like delay, packet losses, These are like some. These are the network uncertainties. So system should be tolerant to this type of network uncertainties also. So designing such a resilient control is really a challenge. Just tolerant to all type of sensor and actuator faults as well as network faults is really a challenge. So incorporating this network part. Well, previously actually people are designing the control based on a physical model of the system. Presently, right now, people are modeling the cyber part also, not only the physical part of the system, but the cyber portion also. So this has paved way for the emergence of the cyber physical system. So this, because we are looking at the cyber and physical model, and based on the cyber physical model, we can design the control algorithm. So in that case, we can go for resilient control. So next is weight, like dynamic weight allocation for different farming behaviors and runtime. I told you behavior-based approach. Multiple agents have been deployed. They are trying to mimic different farming behaviors, flock learning, path following, collision avoidance, obstacle avoidance. So all these things should be taken care of. Finally, the agent has to continue with the mission also. At the same time, they have to take care of they have to avoid obstacles. They should not collide with each other. They should follow the path. Suppose the leader follower-based approach, they have to follow the path of the leader also. Multiple objectives are there, but at the same time, it has to move, it has to navigate. So final control trigger given to each agent, the weighted average of this is basically the weighted average of all these type of behaviors. But this, how much weightage we should give for each behavior. So that is basically making the decision making process is basically a real challenge. Dynamic weight allocation, the decision-making process of allocating the weights dynamically to each swarming behavior, which should be given preference. Some cases, obstacle avoidance is more critical than collision avoidance, but some cases, some instance, we can say. So collision avoidance may be more important than obstacle avoidance for the instance. So the weight has to be dynamically allocated depending upon the conditions. So this is basically this decision-making process is also really challenge. So the formation control approaches we can broadly classify into time triggered and event triggered approaches. So we want to control this position or velocity of a mobile robot. So we need to key this. We need to control it. We can control it every sampling instance. Every sampling instance we can control it. So that's type of controls we're calling as time triggered controls. We are giving the control triggers at every sampling instance. So there are many approaches available: feedback, linearization, backstepping, optimal control, sliding more approaches. These are now some of the names. So if anybody wants to know detailed about this, any of this approach, I can. So these are some of the approaches. I'm basically using sliding mode based approach. So which I'm trying to discuss in the case study part. That is on sliding mode based approach. So event triggered approach means we are not giving the event triggered approach. We are not giving the flow. Event triggered approach. We are not giving the control triggers at every sampling instance. So at a certain event instant, whenever there's a criticality comes in the system, so then only we are giving the control triggers at in event triggered control approaches. So these are like designs. So two types of broadly designs. So event triggered approaches are more optimal. So I have one case study is on event triggered approach and case study. Hello. Hello. Hello.
Continue, sir. No any problem.
Okay.
Continue.
Yeah. So. Okay. So actually, I'm going to discuss two case studies also finally, two blocks which I've done. So one is one is in time triggered approach based on time triggered approach, and second one is based on the event triggered approach. So then again, of course, case studies on fault tolerant approach also, actuator fault. In case of actuator fault, how we can define the controller. So that also been included in the case study part. So fault tolerant control is very important. So there are many approaches are available. We can design the controller such that it is tolerant to the actual sensor fault. Even if a sensor or actual fault happens, the system can tolerate, adapt to this particular situation and continuity. So this is basically comes in design part. So network fault tolerant. Of course, if you have some network faults happening, so we can go for a hybrid approach. We can, based on cyber physical models, we can design a network resilient control algorithm for system. Then fault formation, so especially sometimes actually the faults are very critical. So multiple robots are there. Some robots become completely faulty on runtime. So it's quite difficult to go with the fault particularly continue the mission. In that case, we need to isolate the agent. So the formation should be formation isolation is also important in that case. So even if one of the agent is isolated from the formation, the rest of the agents should be able to continue the mission. So that is another approach in resilient. So there are some of the references also that will show towards the end in each of the domain. These are some of the time-triggered approaches. You can see some of the feedback linearization. I don't know how many of you are familiar with this approach. So this is a nonlinear control approach where we are commonly used. So we are designing the control algorithm such a way that when you just plug into the system behaves like a linear system. So we are linearizing the system to feedback. Backstepping is another approach, the approach. The optimal controls are also available. So we are controlling the system such that it will optimize the energy consumption or the minimum time or in optimal control. So model predictive control is another control where there is a future planned control action. So we will forecast the future actions, and based on that we will use the control to person model predictive control. The sliding mode control is a nonlinear control approach. So that's been broadly been used. It's based on it's a switching control, variable structure control. The control algorithm has different structures depending upon the operating conditions. So that's very robust algorithm, sliding mode control approach. So it is very much robust to the system uncertainties. So this is a sliding mode approach has been used in the case study which we are going to. So I'm going to I told you this multi-robot system, multi-agent system is very broad. So, but the case study I'm going to discuss right now is based on wheeled mobile robots. So having two-wheel mobile robots. So this one dummy wheel. So this is the model people usually commonly use for designing this multi-robot algorithm for the two-wheel differential driven. So differential drive mobile robot means, so we have two wheels, so the two wheels can be separately controlled. So separate motors are there for different different wheels. So it can be controlled separately. Another type of robot is car type robots. That type actually we cannot individually control the wheels. So in this case, this is a case where differential driven robot. So we can really control it, and it's non-holonomic robot. That means we cannot move sideways. Sideways motion is not possible for this type of lateral motion. So longitudinal direction is the direction where actually where that L is marked. That is the longitudinal axis of this robot, and in that direction robot is navigating. So this wheel axis, that's lateral axis I'm calling. So this along lateral axis motion is possible. So that's why it's called non-holonomic robot. This is a basic model which we derived. X and Y is the position of this robot. First, actually, we are defining this XY position with respect to a point A. The point A at a distance of L meters from the center of gravity of the body. So that is L is the distance from the off-axis handling point from the COG of the bot, and omega is the turn rate, angular velocity of the robot. Theta is the turn angle, instantaneous turn angle. V is the velocity of the bot. X and Y are the XY positions, and the XY position X dot and Y dot are the velocities, velocity component along the X and Y directions. So this is the commonly used model. This is called unicycle model. So unicycle model means we are considering while designing this, we are deriving this mathematical model. We are considering it as a cycle with one wheel, because we are considering only one velocity v. Okay. So we are not individually considering the velocities of both the wheels, right wheel and left wheel. We are considering it is having only one wheel, one velocity we are considering. That's why it's called unicycle model. So this particular model, that's the name of the model. So well, you design the path planning of this multi-robotic system. So there are many approaches are available, and just for example, I'm just sharing two methods. So path planning part of multi-robotic system. One is a geometric approach. So we have multiple robots. Suppose multiple robots need to make a. Suppose there are 3 robots. So it need to make a just like this. So for example, simply 2 robots. So just one robot need to follow the other robot by maintaining an offset between them. So that case, separate one approach is separation. That means actually only the distance is the follower robot is following the leader, maintaining this particular distance. Only the separation. Next is separation bearing. Separation bearing means the follower robot is following this leader and taking care of the angles also. The bearing angle you can see from here. So this apart from this separation distance, the bearing angle is also been controlled. So geometry, based on this formation geometry, we are planning the path in this geometry of the formation. So depending on the formation, we can decide. Hello? The next approach is artificial potential field-based path planning. So artificial potential field-based path planning is actually some of the equations are here. So this is some of the this I'm not going to that equation. So this is a particular kinematic model. So based on a kinematic model, we have designed the path. So in geometric approach, this much only. So based on geometric shape, we're designing the path. Based on we need to maintain the separation distance on the bearing angle. So artificial field-based path planning scheme. So we are making this velocity of the agents to follow the gradient of a potential function. It's a artificial potential function is a mathematical function. It's having 2 parts. So one is the attractive part and second is the repulsive part. So we are enforcing the velocity of each agent to gradient, the gradient of energy function or artificial potential function we are calling that. So it is having 2 parts. One is the attractive. One is called attractive. You can see that is that in this equation you can see we are trying to make the relative motion dynamics of ith agent respect leader to follow the negative of the gradient of a potential function, where j is a potential function. So this Zi means the ith agent position. Zl means the ith agent a leader position. Zi dot means its velocity. Zl dot means the velocity of the leader. So that means Zi dot means Zl dot is the relative velocity. So of course, relative velocity has to follow the negative of the gradient of the potential function. So this potential function is supposed to have unique global minimum, and again, it is supposed to be at the desired separation. So this potential function is having 2 parts. One is attractive part, and the next is the repulsive part. So when these agents are far apart, the attractive part of this mathematical function will predominate. So that it becomes closer towards each other. And when these agents are very close, the distance between agents are very small. In that case, actually, the repulsive part of mathematical function will predominate. So that actually it will be repelled away from each other. So that actually, and finally, the attraction balances the repulsion, and the net potential function value will be equal to 0 when this agent is at desired distance separation with respect to the neighboring one. So this is the mathematical concept. So the gradient. So these are some of the type of examples for this potential function. Simply suppose we have simply one agent, simple one robot. Suppose for example, we are taking simple case. One robot needs to go to goal position, X goal. X is the actual position of the robot. Next goal is the goal position. And even we can say simply this velocity can follow the gradient of this particular potential function. So this you can see it's a positive definite function. So this X goal is the goal position. X is the active position. So next is suppose if you have an attractive and repulsive part. There are some of the examples. One actually is proportional to the one will be one. We can see one part. The attractive part will predominate as the distance is very high. Y is basically distance between the agents. In this equations, Y is the distance between the agents. A, B, C are some parameters. They are tuning. So this desired distance in agents is decided by these values of A, B, C, etc. So there are some tuning algorithms also to tune these parameters, ABC parameters. Why is the distance between the agents? So finally, when this agent's distance is very high, so the attraction will predominate. When it's very small, the repulsion part will predominate. So we can design this path based on, this is these are the two examples I can show in path planning part, but there are many path planning algorithms that are available for multi-agent system. So this is a path planning. We can plan the path of the agents. What is the desired path to be followed by each agent? But finally, for this, but the agent should follow this path. We have to ensure that the agent should follow the path being designed. So we need a controller for that to enforce. So here you can see that I'm designing the reference trajectory, desired trajectory for the relative velocity of different agents in the system. So you can see that in this equations, you can see the relative velocity is supposed to follow the negative of the gradient of this function. So I'm designing a reference trajectory for the relative velocity of the agent. So now my task is to make this relative velocity, actual relative velocity of these agents to follow that desired path. So I need to design a controller for that. So of course, for disturbance rejection. Otherwise, we can directly feed this desired velocity to the system and to make this to follow, but always it may not follow that because disturbances can happen in the system. So for ensure disturbance rejection, we need a controller. So in this case, I'm going for a sliding mode control algorithm. So I don't know, let me see the time. So I can complete this algorithm or not, I don't know, but I will just give a short introduction to sliding mode control because there are many approaches. So in this one, I'm just particularly looking at the sliding mode control approach for controlling different agents, design the control algorithm. So sliding mode is basically switching variable structure type of control. The control algorithm has different structures based upon the conditions. So here, and this logic, sliding mode logic. So switching logic has been used widely for many applications. Then actually, just look, consider the system. X dot f of x, u system equations give x dot f of x, ut. X is the system state, u is the control input, and the t is the time instant. So if it's a nonlinear function, so you can see here u is u plus, and s is a switching function. S is a switching function. It's a function of x. X is basically state, system state. U is the control input. By controlling u, we can control x. So for you can see that u is u has two types, u plus and u minus. U plus is a function, u minus is a function. Both are functions. I just represent by u plus and u minus. They are not constants. So these two control laws are here for u. For s is a function where s is greater than 0, where the s value is positive, is control law is u plus. Control function is u plus, and control function is u minus when s is negative, s is less than 0. So s is equal to 0, we are calling it as a switching surface. So we are trying to enforce the trajectory of the system, x trajectory of the system along desired surface. So through this sliding mode logic. So s is equal to 0 is called switching surface basically. And if you can see that if s is supposed for a particular x, for a particular operating condition for an agent or whatever be the system, for a particular x, suppose s is greater than 0, s is positive, then the first law is triggered, u plus is triggered. So s is greater than 0. In that case, we are actually controller u plus is designed such a way that s dot is if s is greater than 0, s dot is less than 0. So that way, actually, the control law has been designed. Yes. So for design the control law, we have used the reaching law. Below, you can see reaching law to enforce the trajectory. The sliding surface is minus of k into sine of s. You can see when s from this equation s dot is minus k into sine of s. You can see when s is positive, k into sine of s. When s is positive, the s dot is minus k, and s is negative, sine of s is minus 1. So minus of k into minus 1. So it is k. So s dot is positive. When s is 0, when s dot is 0. So that means s and s dot has different signs, opposite signs. So when s is positive, then s dot is negative. So in that way, so we are designing this u plus and u minus such a way that this law is satisfied. S dot is minus k into sine of s. That law is satisfied. So we can ensure that always S and S dot has opposite signs. So when S is greater than 0, suppose for a particular operating condition, when S is greater than 0, U plus is triggered. And again, now we know that if S is greater than 0, S dot is less than 0. S dot is less than 0 means the S value, S function, the S function is decreasing. S is decreasing basically. That means finally it decreases and come at a point, it keep on decreasing, and finally S becomes less than 0. When S becomes less than 0, the U minus is triggered. So this trajectory will move to the other way. So now from the figure, you can see that when S is greater than 0 region, this when this U plus is triggered, then finally S dot is less than 0. Then finally, I can say that S dot becomes less than 0. Then U plus is triggered. So in this way, the trajectory will flicker about this point S is equal to 0. So always we can ensure that if you are designing the control law, such a ensuring this reaching low, S dot minus K to sign of first, you can always ensure that the trajectory of X will always stay in this particular region, S is equal to 0. So we can make this trajectories to confine to a particular region in the state space. So if you can follow this logic. And there are many methods to design the sliding surface. So S is basically called sliding surface, switching surface. So we are defining the switching surface for a system that can be a linear function, nonlinear function, mostly nonlinear functions. So this and again there are different methods for designing the sliding surface. So depending upon our objectives, we can choose the method. So this is one of the example we can design sliding surface. So S is equal to d by dt plus lambda. Lambda is called slope. This is the slope of the sliding surface. X tilde is the error. So we are trying to in this control algorithm. Well, my application is to design a control. Switching sliding mode logic has been widely been used in many applications. So my application is to design the control law. So my aim is to make this error between this actual desired trajectory to 0. So my switching surface is a function of error. So finally, when these trajectories will converge to this origin, trajectories converge, as the trajectories are staying in the sliding surface, f becomes equal to 0. When this is a function of error, finally error also will become 0. Suppose if you are design the sliding surface such a way that it's a function of error. So you can see that example here is S is a function of x tilde. X tilde is equal to x minus xd. X is the actual trajectory. X is the desired trajectory. So this is a very broad topic, so I'm just skipping this portion. So I think actually you get a rough idea about this logic. So we can design this U plus and U minus based on this reaching law. So the main design steps in sliding mode control is design the sliding surface, then execute that in the controller to enforce the system states to reach and remain on the predefined surface within the state space. And this is very robust algorithm, but one of the disadvantages is that this trajectories will always flicker about the surface, switching surface. So because of this variable structure of this controller, of course the flickering can happen. So that is one of the disadvantages, but there are many methods to mitigate this charging issue in this sliding control. The main research challenges, these are like not needed. So charging mitigation, fastener, adaptation, fuel requirement. So there are many research challenges if you want to work in sliding mode control. So anybody wants to know more about sliding mode control or any of these control techniques I've shown in the formation control approach, I can explain. And even I can give the reference also for area, control approach. So the first case study we are looking at the fault tolerant multi-robot coordination. So one of the case study. So here we are trying to control multiple land rovers. So based on sliding mode based approach, and we are using artificial potential field based path planning, and it is a fault tolerant control. So system is able to cope up with the actuator faults in the system in such a way that it's been designed. So before going to this, I will show one video. The video is basically the implementation. So this algorithms, this case studies, two case studies I'm going to show. One is the fault tolerant control, multi-robot coordination. Second one is the consensus based, a graph based approach. Multiple robots are here. This following, it is making a formation based on a graph. Okay. So based about this approaches I've implemented. So this video, I will show a short video. This so this is a basic. There are many algorithms are being implemented. So this case, so this is here you can see one leader and one follower. A simple case. Where actually one leader is following the follower. That's it. So for different manuals, we are testing velocity, acceleration, deceleration, right turn, left turn, and all this. Some test cases are being tested here. So turn maneuvering and velocity maneuvering we are checking. If the front one is leader, back one is the follower. So the experimental setup is here. You can see here two Pioneer robots we are having, and they're having onboard computers and sensors. Basically, we are using our this one sonars we are having. Then camera offboard. There's an offboard camera here because for initial positioning, finding the initial position with agents, we are using an overhead camera. And Aruko markers are being fixed over this. So based on this marker, so marker IDs are the different markers have been given, been based on different robots. So and again based on this, the initial position between the agents can be predicted, can be computed. And we are using on runtime, we are using odometry to find the relative position in this case. And both of them have onboard computers, so it's completely decentralized. And we are having a local network here. Robots are communicating through Wi-Fi, and we are having a local network created, and we have generated some static IPs and assigned for each agent, so that actual data coming from each agent can be demarcated based on. These are like different algorithm. Fast adaptive gain. First is fast. Next is fuzzy based algorithm. Fuzzy based Vladimir control algorithm for simple case. Simple two robot case. One robot is a leader. Second robot is just following the first robot. And they are testing different things. Acceleration when it's accelerating right now. Then it is to turn manners, right turn and left turn. And velocity, basic velocity maneuvering, velocity and turn maneuvering also. These are the four cases for testing the robustness of the algorithm. These are differential tray robots. So have two wheels and one dummy wheel here. So next is the formation recon. One is a case where robots are making initially one distance separation. After some time it's making one. Initially the robots are 1 meter separation. They're making the 1 meter separation. After that, 0.5 meters. Initially at 1 meter, later to 0.5. So is the video visible? Hello?
Yes, sir.
Is the video clear?
Yes, sir. It's visible. Yes, sir.
Go through three robot case. So three robots. So this is a case where three robots were actually these are dissimilar platforms. This is two similar platforms, two Pioneer robots and one Firebird 6 robots are here. One is the Firebird 6 robot, and two are Pioneer robots. So one leader and two followers. So it's making a V-shaped formation. Okay. So just V-shaped formation, just and testing all the right left minus. The next is the fault tolerant control. So here having the three robots, so one leader and two followers. The robot is between faulty on runtime. So, but still, it will continue the mission with the two robot formation there. Firstly, it was the 2-3 robot, but we can say the left robot has been post doing the stop, so it becomes faulty. And now it is switched to two robot case. But basically, these robots are communicating with each other. But still, even if one is isolated because of the fault, the rest of this agents are may continue the initial information. You can see from this. So this is a similar platform case with similar similar formation, the 5x6 platforms. So making a V formation in this case, similar platforms. Previous case was the dissimilar case, dissimilar platform. Here also you can see all the three robots are on board. That's similar. The Firebird 6 robots, the next robot. Next one, I told you the event triggered control, graph-based approach. So this is both simulation. First I'm showing a simulation using player state simulator. There's a simulator which we can simulate. We can visualize the robots also. That's the player stage. So I've implemented first in that simulator, player state, and later I implemented in real robots and pioneer robots. So this is a consensus-based approach. That means we're having 4 robots. So these 4 robots are making a square shape formation. And again, they are not communicating with each other. Only few agents are communicating. It's basically a graph. You can make a graph for the communication in the different agents. So here you can see, I'm just going to show the simulation first. Here, this is the screen for this one, the simulator. We are having 4 robots. So this one, red one is the leader, rest are all the followers. But the leader is not in the front, it's the back side only. It is trying to make a square shape formation. So now I'm going to disturb each agent one by one. So see how robust it is. It can come back to the position even if it is. I'm perturbing leader first. So I'm disturbing leader first. You can see that within a few seconds it is coming back to the original formation. So once the leader is perturbed, all the agents are affected. So it's been connected to all agents. But you can see one of the deputy 3 is been disturbed. In this case, 2 of the followers are also affected. That means they are connected. So, but they are coming back to the formation within a short span of time. So now I'm going to disturb the next agent. So deputy 1, follower number 1. So you can see that all agents are not disturbed. Only green one is disturbed. That means only green is connected to that. It's following a graph. That's the meaning. So when this green is disturbed, you can see none of are affected. That means it is not sending information to any other, but it's receiving information, but it's not sending the information. That means it's following a graph. So all the agents are not communicating with each other. But here, when you disturb the leader, the red one, you can see that all the agents are disturbed, affected. But still, it's making the formation the short span of time. So this is basically simulation part. The next is the implementation of the same algorithm for the 3 robot platform case. That's regarding intelligent systems and control our idea. So for all the experiments. So here actually it is at the 4 meters distance separation. Final distance separation is 0.5 meters. It's this leader is this one. 5x6 robot. The followers are pioneer robots. So now it's like same type of experimentations we have done last case. This is called the velocity turn maneuvering velocity turn. In this case, this is a little slow because of course the optimal communication. All the agents are not communicating with each other. So the optimal sense, resource requirements, we are trying to implement this. So this is the second case, event triggered. I will explain actually what is this event triggered control. So event triggered means we are not giving the control triggers at every instance, but we are, whenever it is needed, then only we are giving the control triggers. One minute. So the first one which I've shown, the first video which I've shown is on the fault tolerant control. So this for designing this particular control, we have used sliding mode control and artificial potential based path planning. So sliding mode this the blocks you can see sliding surface, reaching low. These are all part of the control low. So these are like the blocks. We are computing the sliding surface, sliding function, then the reaching low part. So this has been finally given to the ith follower. So this ith follower position ZX, Z is the position of the ith follower, that's in sense, and ZD is the desired position of the ith agent that is been given by the path planning module, and Z is compared to ZD, Z minus ZD is error. So we are trying to control the minimize the error between desired and actual position. So based using the controller. So is the error. We are trying to minimize that. And finally, the path plan. The desired path of this each agent is decided not only by the position of that particular agent, but also the neighbor agent. So you can see that ZJ inputs plan. The inputs to the path planning part is ZJ, ZL, and all. So not really ZI. Okay. So this path planning ZI, ZL, and ZJ is needed for designing the path. So this is not this in this artificial pressure-based path planning scheme. It is a one-to-one communication is needed in this case. So we are not going for a graph in this case study. It's not based. It's not a graph-based approach. So so we are designing the basic this one sliding mode-based approach, fast sliding mode-based approach in this particular scheme. So how we improvised research contribution for this particular approach is we've improvised the sliding mode algorithm. We have actually, I have shown as switching low in the sliding mode control algorithm minus k into sine of first. So this is basically this equation, this part will comes inside the control algorithm, control low. So, but because of that sine function, of course, I told you chattering is what chattering can happen. That's one of the reasons chattering is coming inside the happening in system. When a sliding mode based control module, the chattering is happened because of the uncertainties of the system, but sine function will triggers it. Sine function will can amplify that also. So we can actually replace the sine function by hyperbolic tangent function to reduce that. So that is one. And again here instead of k into sine of us, I use minus k into tan h of us minus pi into s. K and pi are control gain constants. S is a sliding surface. So these parameters we are not keeping as constant. We are adaptively tuning. So we have derived some algorithms to tune these parameters k and pi on real time, so that actually system can make adaptive. So we are not pre-deciding the control law, the control law parameters. So we are tuning the parameters of the control law in real time based on adaptive tuning algorithm. So these algorithms are derived based on Lyapunov theory. So the system is Lyapunov stable. So theoretically we have proved that system is Lyapunov stable. And for details on this particular approach, you can refer this paper, my paper. So that's published in IEEE Systems Journal. So that the fault tolerant formation control of non-holonomic robots using fast adaptive gain in DSM6. So this paper discussed about two methods. So one is this adaptive tuning algorithm for the reaching law gain, and second one is an improvisation based on fuzzy logic. So we have replaced this particular reaching law by fuzzy inference mechanism. So fuzzy logic is a broad topic. I'm not going to fuzzy logic. So fuzzy logic is mostly being used wherever fuzziness, vagueness is there. We can use fuzzy logic. So we are replacing this function, this k into sine of us or k tan h of us minus pi s by fuzzy inference mechanism. So that actually fuzzy predictor will predict the control input. But basically it follows this logic also. So this, but again, fuzzy inference mechanism, the fuzzy parameters, pre-tuned fuzzy parameters, again will make the system non-adaptive to system uncertainties. So in that case, actually, we have to make the system parameters adaptive. So we have designed some adaptive tuning algorithms to tune the parameters of the fuzzy parameters. So again, we have developed adaptive tuning algorithms for real-time tuning of the fuzzy parameters. So they are also not constant. So next slide also, these are some details and not some error definition, formation error and all. So this is, I'm skipping this portion. This is sliding surface equations, where many types of methods are available to design the sliding surface for a system based on the model. So I'm skipping this portion also. These are some mathematics. So this is the Lyapunov function we use for designing the algorithm. The Lyapunov function, we have to, while we are designing any control, this is a control law. So the control law we are designing, we have to ensure the system is stable for all the operating conditions, theoretically first. So we have experimentally proved it because we have implemented in real time, but we have to prove theoretically. So theoretically proof we use, we'll go for Lyapunov-based analysis. Details are available in this particular paper. You can go for that. This paper which I have given. So in this paper, you can see the details of this. If anybody interested to see the details of this design, you can look in this particular paper. The details are available in this paper for the design. So this is the Lyapunov candidate being used. So these are the tuning algorithm. Finally, the derived final control law. It's been derived with Lyapunov theory. This is the final result of this. So this is the tuning algorithm for tuning the parameters k and pi. So k dot and pi dot, k hat dot and pi hat dot. So these are the tuning algorithms. So basically, usually parameter updation, usually in sliding mode algorithms, people fix these gains as constants based on the disturbance bound. But in this case, if you are using the algorithm which we are proposing, so we don't want the bound of the disturbance acting on the system. So we can use this tuning algorithms even if you don't know the bound, even if you don't have any knowledge of the disturbance acting on the system. System can adapt to this uncertainties and disturbances like this. So these are those who know the fuzzy logic and may know it may need the fuzzy inference mechanism need a membership function. So these are the input and output membership function which we use. For simplicity, a very simple membership function, but there are many complex membership functions can be used. The rule base and all, I'm skipping this portion. So fuzzy logic for implementation, we need a rule base. Basically, fuzzy logic, we are using an operator knowledge to realize this. Okay. For designing this system, so we are using operator knowledge. So here we are just replacing this k into sin of s function by fuzzy logic, fuzzy inference mechanism. These things I'm just skipping. These are some conditions. So based on the fuzzy rules, different conditions, possible conditions for this, based on the values of yes, different conditions and all. I'm skipping this. So all this portion. So this much, this fuzzy logic can be used. Fuzzy logic can be used to replace this reaching law. So fuzzy based reaching law can be implemented. And in this case, I told you, we have designed adaptive tuning algorithm for tuning the parameters of the fuzzy parameters. So the fuzzy parameters R and pi. So R hat is basically the bit. W1, W2, these are firing strengths and all. Alpha is a constant. So these are the algorithms we derived based on Lyapunov theory. Here also we don't want the disturbance bound, knowledge of the disturbance bounds to tune this parameter, but that is been usually needed for designing these parameters. So I told you this is a fault tolerant control, fault tolerant. So what we have discussed so far is basically a simple control of a multi-robotic system. So here, if you want to make it fault tolerant, so we need a fault detection algorithm. So we need to detect the faults. So once we detect the fault, if it is critical, we need to isolate that particular robot. If it is not critical, it's a simple minor fault. So in that case, we can system, if the algorithm is robust enough to deal with it, so we can go for a fault tolerant control. So here we are using an adaptive control. So the minor faults, it can deal with that. It can deal with these minor faults. So system can continue with this mission even if minor faults are happening to the system with any of the agents. But suppose this is the case where actually minor and major faults can be dealt with. If minor faults are occurring, the system adaptive control will take care of that. The system gains will be retuned and the system will adapt to the uncertainties. But if a major fault is happening, in that case, that particular agent is isolated and path planning module is being updated and the control will make the system to follow this particular path. So in here you can see in this this is the block schematic for the control of the ith agent, fault tolerant control. Here we are having the fault detection algorithm. So each in this particular approach, we are asking all the agents to detect. All the agents have to detect whether I'm faulty or not. So if it is faulty, it will set a fault flag. So based upon the desired measurements on the model, based on this residual computation, so that I will show you. So this residual computation, they will find actually whether this is faulty or not using the available measurements. So based on this, it will set the fault flag and it will communicate this fault flag with the neighboring agents, which is connected to that. So this once it is a fault flag is been received, so each agent will compute this path based on the fault flag. So if the fault flag is been set, that means that agent is completely critically faulty, and that is need to be isolated. So in that case, actually the formation size will be reduced, and path planning has to be remodeled. So the path planning module, the formation will reconfigure, the isolation is happening, formation is reconfiguring. At the same time, the agent should avoid collision with the isolator agent also. So all these things will happen. So these all things are part of the adaptive path planning module. Artificial potential based path planning module will take care of all these things. So fault detection algorithm will detect the faults and set the fault flag and will send it to different agents. Once the agent receives the fault flag, if it is isolated or not isolated, even if it is not isolated, again, it will compute this path planning module compute the result path. So if it is isolated, the particular agent is isolated, removed from the formation, and the rest of the agents will continue the formation. Vision. So and if it is a minor fault, if the fault is minor, the fault flag is not such. In that case, actually, the normal path planning law will be used, but the controller adaptive tuning part of the controller will help the system to cope up with such a minor uncertainty. So to tune these parameters to deal with the uncertain system and retain the stability of the formation even if a minor fault is happening. So we are using a residual-based fault detection. So some residual computation we are doing, and fault flag is set based on residual computation. This I'm skipping this portions. Next is this is a gradient potential. I told you potential-based pathfinding. These are like all our functions. This J is a function that is not been given here. So this F is the fault flag. So del J means the gradient of the potential. So these are different details are available in the paper. So all these details are available in the paper. You can for the paper you can get it. So here having this here also we are using a potential-based pathfinding script. So we are making the velocity to follow the gradient of a mathematical potential function. So potential function is it's a function of the fault flag also here. So when fault flag is in set, the potential function will adjust. So the experimental setup, I already told you what all things have been used for the experimental setup. So here we are using Pioneer P3DX robots and 5x6 robots. So here we are developing intelligence for the system. So hardware has been purchased. So we are developing Cognition module for the system. So they are all are two-wheel differential driven robots with sonars, encoders, a PC running a Linux platform, and we are using player stage for interacting with the sensors and actuators. We are using player stage driver, and we are using local Wi-Fi network. We have created and assigned static IPs to each agents, and using static IPs, we are actually identifying the agents, and we are using overhead camera to identify the initial position. But once on runtime, we are using the odometry. We are using odometry to find the relative position, and you can see that in the video you have seen. There are some black and white markers are being used, be pasted on the top of the robots. So these markers are used to identify the robots. Based on these markers, the distances are being computed based on the Arroco. Arroco's virtual reality library. So these are some of the video images which are shown. So you can see in this figure, these markers have been highlighted with some color, with some rectangular box. Once markers are detected, this thing is visible. The marker ID is visible. These are the experimental results of this. The graphical results of this experiments. this actually, this is the position trajectory. Middle one is the leader, other one are deputy or followers. So this is the leader follower based approach I told you. One leader, two followers. So it's making a triangular formation. So this there are random different positions, and finally it is coming to a triangular formation. You can see the different instances, the positions are marked by. Next one, second one is the distance separation between different agents. Distance separation 1 and 2, 1 and 3, 2 and 3. 1 means the leader, 2 and 3 means the followers. X and EY means error between the error. X and EY errors that is defined here. Then these are the gains. I told you the controller has some gains. So the controller initially been to 0. The value of the controller is initially 0. But we have used the adaptive tuning algorithm to tune this gain. So it automatically tuned the values. So based on the algorithm. So we are giving initialized in a 0. You can see that all figures. So all different gains are settling to different values. Okay. So or desired values. So from 0. So the separation distance, desired separation, it's coming to desired separation distance for case 1, case 2, different cases. We have actually done different experimentations or different cases we have seen what is the distance separation. And it's figure. So next one is reconfiguration. Next one is fault tolerant. I told you fault tolerant case. So 3 robots are here. So one leader and one leader marked in blue, and one in black and red are the followers. So these are the XY position trajectories of these 3 robots. So they are trying to make the triangular formation. So in runtime, you can see that the robot with the red color trajectory is becoming faulty. So in that case, so after some time, so you can see that the rest of the agents are continuing the formation. But actually, this robot is connected to the other agent also, because it is taking the position of this agent also. This black color, the robot with the black color trajectory, it is taking the information from the neighboring follower, but still it is not affected, even if one is faulty and isolated, because it is adaptive tuning algorithm is running the system, and even if one agent has been deleted from the formation, is isolated, detached from the formation, the rest of the agents are adapting to this, are reconfiguring to a two-robot formation, but system stability is not affected because the adaptive tuning algorithm will take care of that. So from here you can see that from the gain plots it's visible. You can see at some instance at 10 seconds you can see that initially the gains starting from close to 0 and it is settling to some value, but after some time fault is happening. It is marked in dotted circle. You can see that's the point where actually fault is happening. One agent is becoming faulty and it is isolated. So in that case, actually you can see that the gains are retuned and the gain settling to another optimal value. So this is the advantage of adaptive tuning algorithm for adaptive tuning the controller gains in real time. Even if faults are happening, even if agent is isolated, the rest of the agents can continue the formation, and if the stability of the system will not be affected because the parameters are tuned adaptively on real time, and even if minor faults are happening, minor disturbances in the form of disturbances are happening, the system will consider it as a small disturbance only. Some minor fault in the system. So that case also, this gains are will be retuned, and system can adapt to this uncertainty by varying the gain, by adaptively tuning the gains. So these are the errors, EX and EY errors for different agents. The first one is for the faulty agent, that's why it's increasing. Second one, the agent you can see, this is the errors, EX and EY along X and Y direction errors, formation error. So this error is supposed to convert to 0. Formation error should come to 0 always, but for this first agent is faulty, so that's why it's going to unbounded value. So but you can see for the other follower, you can see that it always return 0 value. So practically the results, of course, there will be minor variation that you can see. So these are the velocity trajectories, the 90 trajectories. So velocity, you can see that these are a post-fault region. We can see that there's a variation of velocity in that case. So we are inducing a delay also to test the robustness of the algorithm. We have induced a delay because fault detection, we are induced a delay in detecting the fault because it can happen. Once the fault is detected and it's getting communicated to the neighboring agent, so there we can expect a practical delay. So for testing the robustness of algorithm to such delays, we just induced a short delay of few seconds to this. But still we can see that it's converging even if with this short induced delay. So all this case, the next is the event triggered approach. I told you event triggered approach is resource optimal control. So we are using a graph-based approach. So all the agents are not making one-to-one communication, but based on a graph, it's communicating. So from the video, it is clear. So they are making 4 robots are there. One of the robot is a leader, and rest are followers. So in that video, and you can see, and you saw all the agents are not communicating with each other. Only few there is no one-to-one communication. Right? It's based on a graph. It's communicating, and apart from that, there's one more advantage is that for the approaches, we are not giving the control in triggers at every sampling instance. Only when it is required, then only we are giving the control triggers. So that's advantage of event triggered control. So I will tell you what is an event triggered control. We are using event triggered control here. Here you can see from this figure. First one is time triggered control. So system is controlled every sampling instance. You can see system here, one block. An actuator is basically doing the actuation. Actuation is done by an actuator basically. So it's basically a motor, we can say it's an actuator, it's a motor, physical system. Example. So controller, of course, our controllers are mostly computer control. So and again we have a sensor to sense the data. And we are sensing data at every sampling instance, every clock instance we are sensing the data, and we are giving this data to the controller. So of course the controller is giving the control triggers to the system at every clock instance. So this is the time trigger control which we have discussed so far. The last approach is the time trigger control because we are giving the triggers at every sampling instance. But in some cases actually where the robots are remotely be deployed, so where actually our access station is quite remote from this quite remote location, that case delay can happen also. So of course the system should be able to deal with that first type of delays, and also event triggered control can deal with such type of uncertainties to a certain extent. In event triggered control, so we are not giving this control triggers at every sampling instance. We are not giving. So this actually is a block schematic for event triggered control. So we are not sensor also. Sensor is also intelligent sensor. So sensor also not sensing data at every instance. They are sensing data at some. They are sensing data, but they are not communicating the data to the controller at every instance. Whenever it is needed, then only it is being communicated to the controller. Because sensor has computation capability. That's the intelligent sensor, a smart sensor. We can use in that case. So in that case, the sensor has computation capability, and we can decide whether the data is to be communicated or the system is to be controlled or not. So the controller is more intelligent. So controller is not giving the control triggers at every sampling. Whenever it is needed, it is given. Otherwise, the previous instant control is being given to system. System needs an input. System uses the previous control input and continue the mission. But an event is happening. Event is again a mathematical condition again. Okay, an event is happening. That's a mathematical computer, a computational logic, we can say. So then it will compute an event. But an event is a stability condition, we can say. That is also derived based on Leibniz theory practically. So when event is happening, whenever a critical thing is happening, so that case actually the control input has been triggered and it is given to the system. So that means it is not is having non-uniform sampling input. Okay. So this is the case of event triggered control. All the sampling instance we are not giving the control triggers. So in this case, the controller communication with the controller and the system can be optimized. because every instant controller need not communicate with the system, especially when the controller is a remote location. So it's quite difficult to communicate with the system. In that case, if there is event triggered control, whenever it is needed, then only controller will communicate with the system. So same like sensor also. Sometimes sensors are at remote location, off-board sensor. So in that case, actual communication with sensor and controller can also be optimized with this approach. Because whenever it is needed, the sensor will, based on event condition, it will communicate with the controller. And again, with the system also. So it is not every instance we are not giving the control triggers. In this case, this is a resource optimal control. So we are optimizing the resource requirements in terms of sensing and communication requirements. So we are using, so I'm skipping this slides. So these are some of the research challenges and all. So this I'm skipping. So this is the approach, the case study which we are used. We are also we are using sliding mode based approach we are using, but in event triggered control. So different sliding mode algorithm. In event triggered sliding mode control algorithm. So event triggered control means we are again deriving another control logic, event triggered condition based on Lyapunov theory, and we are computing the event at every instant. So if this event is triggered, then this switch is closed. You can see the system deputy. You can see we are trying to. This is the block schematic for controlling the one deputy. One deputy means one follower. So here this use the control input, and TK is the sampling the event instant. So here the zero order hold is using. Zero order hold is having memory. So if the event is triggered, suppose the event is happening, then the switch will closes. The switch, which is marked, you can see that by this dotted line. So it will be closed when event is triggered. That means the signal passes through this line and signal control has been given to the deputy. So otherwise, the previous instant data has been. So this event is been computed. So here also we are using graph-based approach, a consensus-based planning scheme. I'm not going to planning scheme, graph-based approach, and again the sliding planning scheme and sliding mode control has been used to follow this path. And chief means the leader. It's a leader follower-based approach. So they have sensors and triggering condition. So the switch is closed based on event. When the switch is not closed means the event is not happening. I'm just this is the paper. This is available in this way. This is also published work. This work, if you want to know the details of this work, is available in IEEE Transactions and Resource Technology. So this is published in 2019. So this paper details of this design is available. Lyapunov-based design is available for this work. It has been. So this is the paper. So this I've given reference also. This paper towards the end. So this is a mathematical. I'm skipping. So this is the model I used. So this I'm just this is the same model I used also. Unicycle model. Hello, 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 hello.
It's audible, sir.
Yes, audible.
Okay, fine. Okay. Actually, this are comes. Sorry to show this slide because it's very clumsy. These are the three theorems. Basically, these are some of the theoretical contributions in the work. The paper, you can see that. So one is quite difficult to figure out from this. So I will tell you what is that. One is first is for the convergence, stability conditions and all for the first and second one. Third one is like we are giving the triggering at some sampling instance only. So we have to ensure that there is a positive constant or inter-event time should be lower bounded. So there should be a bound for the inter-event time interval. So that also we have proved it. So this is the inter-event interval. So these are the three theoretical contributions, just to show that I've shown this slide. So next is communication topology for the simulation. I've shown the simulation for a forward case. So in that case, one leader and three followers. You can see that here from this figure, this is the communication topology being used. The communication, you can see that it's not two-way communication. It's basically directed graph. So here, this based on this graph, actually the agents are communicating from the leader. all the agents are getting information from the leader. But from here you can see the agent 1 is receiving information from the leader, and 3. Agent 2 is receiving information only from agent 3 is receiving information only from the leader. It is not receiving any information from any other agent. But it is giving the information to 1 and 2 is receiving information from all the agents. So this is the one of the graph which we do. So here actually there is no all the agents are not communicating. So this is a graph. So this is simulation results. Simulation results I have shown. So here actually I've shown the simulation for agent case. I've disturbed these agents in between. So even if I'm disturbing the agents, it is coming back to formation with a short span of time. So this from this figure you can see, I've enlarged, magnified this image. You can see the magnified portion of this. This is the magnified. This region is magnified here. So here actually these are the trajectories, XY trajectories, X trajectory, and there's a Y trajectory of the different agents. If it is perturbed, so it is
Automation Studio, Sunil Core.
So these are the sampling instance. So sampling instance you can see here. The sampling instance are there's a positive lower bound for the intervening interval. So you can see from here. These are discrete. So these are the sampling instance we have recorded. Even if it is dark in color, this is magnified here for sampling instance for each agent. So this is. So these are the next one. Here, this is the measurement error risk. So error, the spikes you can see at point where we're disturbing each agent. I've shown the video. We are disturbing each agent at some instance. So at that instant, actually, this error is spiking, but still it's coming back to 0 within short span of time. So this is the control graph used for 3 robot case real-time implementation. So 1 leader and 2 followers. So in this case, actually, here also you can see that there is no complete point-to-point communication. So this is the taped video images. We have seen that video. This is the experimental results of this. This is the experimental result of that 3 robot case for X and Y. They are making a triangular formation. X and Y positions. There's a velocity trajectories for this agents, and this is the error. This is the triggering instance. You can say the triggering instance. Triggering instance means instant at least the controller is giving the control inputs. You can see that all the instance controller is not giving because whenever it is needed, whenever event is triggered, then only the control input is being given to the system. That is clear from this. So it's purely event triggered control, resource optimal control. So these are some of the experimental results for different test cases, like actually different distance separations we have done. So for different distance separations we have done for in real time. So perturbing different initial perturbations, the experiments are repeated. This is a comparison result. So justify your contribution. So I'm skipping this questions. So this is basically here I have discussed about the two examples as well. Sir, always. Hello.
Yes, sir. Please
Hello?
proceed.
Okay. So these are 2 algorithms I've shown. Both are model-based approaches. So, but we can look into. There are many approaches based on heuristic algorithms like neural network. Purely fuzzy-based algorithms are also available. So here we need a perfect model. But since we have used Sladimer control, it can deal with modeling uncertainties. Not a Sladimer control, we have used adaptive tuning algorithm. We have used adaptive tuning algorithm for tuning the gains. So the modeling uncertainty, it can deal with the uncertainties of the system. And event-triggered control, we use so the resource requirements can be optimized with this event-triggered control, communication requirements, and the sensing requirements can be optimized with the event-triggered approach. And again, inter-execution time is lower bounded. That's what the article proved. So this called Senow behavior. This inter-event interval, there is a lower bound for inter-event interval. Otherwise, actually, this infinite number of switchings will happen in the with a short conductance. So that's called Sino phenomenon that can be avoided. So these are some of the publications based on this. Actually, the talk has been but for details you can refer this papers. And first paper and the fourth one, first paper and the second paper, first and the second journal paper. These are two papers which are discussed here. So, but all these works we use at least misalignment control and this one. What is that? Artificial potential function. And even the book is also available, Intelligent Control Robotic Systems by CRC. So press. So this book has been published in this Feb 2020. So this book also covers the this particular multi-robotic system in very broad sense. So this book covers not only multi-robotic system, single robot case, even visual perception, grasping, manipulators are also been covered in that. So, and apart from that, vision part is also there. Then human tracking by robot is also included in this one. Intelligent control techniques of different robotic systems, multi-robot and single robot, mobile robot, as well as for manipulators. But aerial robots are not covered in this book. You can refer this book also if it's available. So these are some of the papers and these are some of the conference papers and all, journals, conference and all. For details, you can refer. So thank you so much for your patience. So that's with that, I'm just concluding this session. So I have discussed only two techniques, so these two case studies. So, but this is a very broad area, and even I'm concentrating in the control portion. There are many a number of sub areas in this domain. So this is only control cognition part that discussed. That's model-based approach. So anybody have any doubts or? Hello?
If participant is having questions, they can raise their hands. So we will allow you to ask the questions. Any participant is having question that he want to ask. Any questions? So, sir, I want to ask one question. Regarding coordination of multi-robotic systems, what different types of controllers are used now, and what programming language is there are any programming languages that are used as of now, recent or advanced languages and control.
Next question you asked about different types of control. So part of that control techniques, this valuable control is implemented, and in aerial robots also it is very. We can always ensure a stable performance, very good performance with this valuable control. It's one of the robust techniques is widely used nowadays. Model-based control. So, but neural network-based approaches are also available because sometimes some robots are quite difficult to model. So models are not available for all types of robots. So, but this simple robots and some type of aerial robots, even this is easy. So in such case, we can go for model-free controllers. So we can use for data-driven, based on real-time data. So the data-driven models or data-driven controls can be used. Neural network-based approach or fuzzy logic-based approaches are also available. Neural network and deep learning is not possible. Deep learning is also can also be used because nowadays hardwares are very advanced. So of course we can use deep learning-based algorithm. Of course, in vision part, people are using deep learning-based algorithms for sensing, vision-based sensing. So, and the second thing you asked is about the programming language, which we have used C++ for implementation, and Python is also being used. Python is also Python we are using. And again, player stage, I told you we have been used a player stage for interacting with sensors and actuators. So we have the player has their own APIs and all, but we can ROS also. People nowadays are using ROS also. ROS also been used.
Okay, thank you, sir. Anybody else want to ask question? participant can unmute themselves and ask if they want to ask question, they can ask. You can raise your hands also. Yes.
If you want to combine the obstacle avoidance as well as this formation control, what kind of algorithms you can use?
Obstacle avoidance with which one? Obstacle avoidance with?
With the formation control. Hello.
Okay. Yeah, I've shown you. Yeah. Am I audible?
Yeah.
Yes.
Hello?
Yes. Yes, sir.
Actually, we can
Yes, sir.
combine. We can combine the obstacle avoidance. I shown actually with that when one slide I've shown. We can combine it. Obstacle avoidance is not shown, I think, here. But there is another potential function for obstacle avoidance. I think I forgot to put that. But there is a similar obstacle avoidance function, objective function. So, sorry, potential function. So we can add it. So net potential function is basically the sum of these three. Okay, we can add these three potential functions. Suppose we have multiple objectives. One is goal seeking, second is obstacle avoidance, and third is collision avoidance. In this example, I have shown first one is for goal seeking, reaching a goal. Second is for the collision avoidance. So this, if you want to implement both, my net potential function is sum of these two. I will take the gradient of these two, and net potential function, and make the velocity follow that. If you have obstacle avoidance, I will include that obstacle avoidance function also. If you want to know the obstacle avoidance function, you can refer my paper. I'll show you this reference paper. This precisely in this. I'll show this paper. This paper you can refer this paper. Actually, journal paper. In this paper, obstacle avoidance functions precisely given. I forgot to put in the slide. Okay, so you can see that. So we'll just we can club it as many number of potential functions depending upon our objectives.
Thank you, sir. Thank you so much.
Anybody else from participants
Yes.
want to ask question? Anybody else from participants want to ask question? Please ask.
Sir, is there any open source platform to implement these algorithms?
Yes, player stage which I've shown is an open. Hello, yeah. Actually, I've shown this this video. And in the second video, shown essentially simulation. So that simulation. Hello.
Sir, continue now.
Yes, it's audible, sir.
Yeah, actually, that simulation video shown. So that is a player stage. Player stage is an open source. We can implement in Ubuntu. So you can install it. So and again, there are other open source platforms like actually Gazebo we can use. And second thing is for multi-report, mobile sim is another platform we can use it. So these are all open source. You can install Ubuntu or whatever Linux platform. It's very stable and you can implement everything. So it will work like real robots. You can visualize it. These are emulators. You can see this. You can visualize these bots on screen, and these are like actually we use this player stage because we can use the same code which we where we the simulation code in this real time also if you are using this type of platforms because it is like it is the model is almost close to realistic system. Mobile sim is one example. Mobile sim is one thing you can use. Hello. Hello.
Anybody else from participants? Please ask question. If anybody has a question. Okay, so should we end the session? So at the last, I will say vote of thanks to Mr. Nair, sir. So the session was very interesting. So it was giving the new. I think it is the new area of the research, and lot of things have to be done in this area. Okay, so I On behalf of our mechanical department and ENTC department of NBN Siyagad School of Engineering, I must be very thankful to Mr. Dr. Nair sir for sparing his valuable time with us and sharing very valuable knowledge to all the participants. So thank you once again, Dr. Nair.
Thank you.
Dear participants, after this we will have a second session. So after 5-10 minutes, this session will start.
Thank you, sir.
Okay.
Yeah, thank you, sir. Thank you.
Jadhav sir.
No, thank you very much. Nair, sir, thank you very much. So it was a wonderful session. New dimensions with reference to automation and mechatronics. Thank you very much for accepting the invitation. Thank you very much, sir.
Thank you, sir. Thank you so much.
Thank you.
So don't log off all
Shall I disconnect?
participants. Yes, you can. Next session will start within 5 minutes, 5 to 10 minutes. So all of you can stay log in. Welcome Praveen Bell sir. We will be starting session in the 5 to 10 minutes. Okay.
Hello,
Sir,
this
are
is
you?
Praveen.
Yes sir. We will be starting in 5 to 10 minutes. Okay.
Yeah, make it 10 minutes. We are online only. Yeah.
Yes. Chore sir is there, or
It's
you are
coming into the
yes. We will be starting for 5 to 10 minutes. Okay.
Okay.
Sign-in, sir. You
Yes.
can display
Please.
the PPT.
Okay. I will display.
Hello.
Sir, link of the feedback is not there.
It will be shared on Telegram group.
Still it is not there. Thank you.
On my already. Okay.
Jadhav sir,
Yes.
the link is not available on Telegram. Can you please?
I think she put
Yeah.
here, na? So this is a blank slide. Yeah. Double click. Delete करके put your image in there. Okay. We have time. 7 minutes.
If Saure sir has arrived, then we can.
Yes. Good morning.
आलेत का चोरे sir?
Oh.
Okay. Nilesh Patil sir, should we start?
He told me to wait for 7 minutes.
ठीक है, okay.
Sainath sir,
Yes.
we'll start at dot 11.
Okay. I will start introduction at dot 11. Then after that, both of them will continue. Session will be continued. Okay.
Sure.
Okay.
My screen is visible to you.
Now, presently I am presenting. Okay. So after introduction is over, I will give access to you to present. Okay.
No problem.
So should we start now?
Yes.
Okay. So welcome all participants. Welcome Mr. Sunil and Mr. Praveen from the Indiasoft Technologies. They are the speakers for today's session. So I will briefly introduce both of them. So first of all, I will introduce Mr. Sunil Chore. So Mr. Sunil Chore, he is working as a country head at Indiasoft Technologies Pune Private Limited Pune from 2004. He is pursuing PhD from Agriculture Crop Supply Chain Modeling and Simulation. He has completed his MBA in Operations and Marketing from Anna University. He has also completed Master of Engineering in Mechatronics from Siegod College of Engineering Pune and BE in Electronics from VIT Pune. So he is also awarded with the DT Maharashtra. He is awarded with a certificate from DT Maharashtra for his valuable contribution in technical education. Also, he has been awarded with the certificate from Lama Para International and Sakai Foundation for extending his social service to needy during COVID pandemic. During this, I saw his various posts during these 2-3 months regarding the various social activities that he was carrying out. He has worked as a resource person and or speaker for around 150 faculty developed programs or workshops for faculties and students. He has a diversified knowledge on various modeling and simulation softwares. He has digital labs in various engineering colleges, skill development centers, ITIs in the field of mechanical, electrical, ENTC and chemical. He is also motivational speaker. He writes column on the entrepreneurship development and career guidance. He has published various articles on his blog www.sunilchore.blogspot.com. He is also active member of NGO, that is a Vidyarthi Sahayak Samiti, Pune, providing hostel facility for around 800 students. He is alumni of that hostel. He is also member of NGO, that is the Samvedna. It is the sister concern of Sahyadri Hospital, and he has also worked as a corporate consultant for various organizations like LIC and Bajaj Alliance. So this is the introduction of Mr. Sunil Chore. The next speaker is our Mr. Praveen Bell. So he is working with Indiasoft Technologies Private Limited as a director and chief technology officer. He is working there from 1997. He has completed his BE from Industrial Electronics from Bharati Vidyapeeth College of Engineering Pune in 1991. So he has around 30 years of experience. He is working. He is handling all pre and post technical aspects of simulation software products like simulation software for fluid power, CNC power plant, robotics, FMS and CIM. So he is a multi-skilled and multi-talented personality. He is exposed to various activities or departments of the organization such as marketing, sales, HR, administration and technical support. He was from the inception of this Indiasoft Technology, this company that is the Indiasoft Technologies Private Limited. He has worked on various software such as AutoCAD Mechanical Desktop 3D Modeling, 3D Studio. So he has also technically handled CAD pipe software. So it is a piping software. Promise, that is electrical software. Softcast, that is a software for casting and simulation. MATLAB and Simulink. Then he has also hands-on automation studio software. He will be delivering some case studies on the automation studio. Then he has handled team for development of web-based sales and management. He personally created the website for the company. So in short, he is a multi-talented and multi-skilled personality. So this is all about the introduction of both the speakers of today's session. So I will hand over mic to the Mr. Praveen Bell. Praveen sir, unmute
Yes,
yourself.
Yeah.
I will.
Can we share
Now
a
you
screen
can.
from here?
Yes. Now you can present it. Use.
Yeah. Arjun, can you see the screen? Can you see the our screen on your machines?
Yes.
Yeah, I'm Sunil Chore now.
So
Hello.
go to slideshow. Go to slideshow. Screen is visible now, but it is
Yeah.
not.
Is this okay?
Yes.
Yeah,
Now
it's
full
okay,
screen
sir.
is visible.
Fine. So I'm Sunil. Good morning, all of you.
Good morning, sir.
Good morning.
Shall we start?
Yes.
Yeah. So with me, Ravin sir is there, and initially I'll be introducing how Automation Studio is going to complement you in this pandemic situation, and especially what subject you are teaching, in which domain you are working, how Automation Studio is going to help you out. Topic of our FDP is mechatronics and automation, and obviously right now we all are sitting at our home. We have limitations on our day-to-day life, going meeting students, and in these cases, I mean, many businesses are opening nowadays, but there is a huge block on educational segment because it's in mass. So everybody would not like our students or their children to come to the schools, to colleges, and take their day-to-day activities of learning. So in this situation, we can't just be a watcher, or because of such a kind of a condition, we can't sit idle. So first of all, I'm very thankful and would like to congratulate NBN College and entire Srinagar society. They are conducting such a kind of a program and giving us an opportunity to tell them that what all are those things are available with which you can still work sitting at your home and getting your technology at your fingertips. So how is this possible? Automation Studio and our today's topic, they are, I mean, we cannot separate them from each other. I'm going to tell you that how we are going to showcase this in detail, right from words of what is automation, mechatronics, and how entire these things are in day-to-day life, how this has covered our life also. So when we talk about engineering as a college, definitely our students think that what are the placement opportunities. Now we are going from this phase which is very critical. Nobody knows what is going to happen tomorrow, and most of our equipment today, if you see in market, many our equipments are automated, and right from dispenser, automatic hand sanitizers, if you see everywhere, automation has placed a very key role. And what is this equipment, what all are these instruments? They are the gift of our mechatronics or automation domain applications. So entire world has stopped, and our automation and mechatronics are those applications are coming to their help. So this is the proud feeling for all of us that with the technology we can even give solutions to the entire world with the help of this automation and mechatronics technology. Now how it is going to be, I mean, how it is going to possible, how people have taken their foot to fight against this, and slowly I'm going to cover that how it is even taken into the depth. After this session, Praveen Bell, our CTO, will take you into the detail of the product. Before I go to the product, I would like to show you the tree structure of this Automation Studio and current topic and current FDP. A lot of your other faculties are going to talk on detailed programming, computer aspects, control aspects. Here we are going to take you your at very basic terminologies, because most of us are teachers, and to make these terminologies too clear to the students, it is very important to know the basics of mechatronics and how Automation Studio is going to play key role in automation and mechatronics. So this is the wheel, whereas you can see so many branches are coming together to become a full-fledged mechatronics system. In Automation Studio, we have so many libraries, and those all are at your fingertips. You have to just drag, drop, and build your circuit the way you do your Rangoli in your home. Similarly, it is as easy to that. So if you see in today's scenario, even getting one component from the market is not possible. Forget about purchasing it. Forget about buying cost of that particular instrument or equipment or component. Here, more than 5,000 components are available at your computer. You can just drag, drop, check your system, check your equipment, test, and simulate it. So this is the best gift of simulation as a technology, that you don't need to put money on your equipment. Still, you can try out various experiments in virtual environment. So this is why I generally keep on talking wherever we conduct FDP. Most of people we get hurdles. नहीं हमको practical करके होना है. We have to learn practically, and there is a lot of resistance comes from the faculties that yes, we need to fill it in on hardware. Now you must have all realized what you were talking or all other people were talking, that no, we want hydraulics kits, we want pneumatic kits, our students should go work on that kit. We never opposed that. We were right from first, we're telling you, while at syllabus committee formation meeting also, wherever it is possible, we always try to give them help, that my dear friend, this is not replacement to your hardware. This is a complement to your institutes, because you are not, I mean, for 60 students, for 100 students, are you going to purchase 100 hydraulics and 100 pneumatic kits? But it is very affordable that you can buy this software and work on all experiments virtually. Once you are ready with your confidence that yes, this circuits is working properly, then you can easily ask your students to perform experiments on practically or on your trainers. So right now, all you people have realized that how key important role is going to play or is being played by this virtual software. Praveen Bell sir will give a very interesting simulation circuits with which you will be able to feel as if you are working on those products or all those processes online. I'm very glad to inform you all that recently Automation Studio and IndiaSoft has given a very good hand to faculties by releasing their web licenses. So all dear faculties, it's a huge important news for all of us that our students sitting at their own home can perform experiment of bottle filling plant. They can perform the experiment of load testing on their actuators. They can perform PLC's experiments sitting at their own places. Faculties sit at his own places, and they can monitor how these students can perform their own practicals sitting at their own places. So this is the beautiful gift from Automation Studio to the faculties of automation and mechatronics and fluid power system, that they cannot compromise losing touch of practicals. Still, they can feel as if they are working on their trainers. So please note this benefit. Now, I will explain you a very basic that most of, even wherever I go for lectures, at the induction program, maybe at the very initial stage of their career, whether 12th out student, passed out students or 10 students, they keep on asking what is mechatronics. Even many of at the time of when we learn, when we were in B electronics, for mechanical, faculties was going from electronics department to mechanical department to teach mechatronics subject. Even in SPPU for last 2-3 semesters, we have been watching that wherever mechatronics subject comes, faculty we used to go from electronics department to mechanical, teach that particular subject, and then be in their own department. Now situation has changed. Now we have to see that what exactly the individual roles of, because I see there are participants from electronics department, there are participants from mechanical department, and how mechatronics and automation both they are going to complement each other. And this is the tree structure, whereas you can see earlier slide what we have shown you, and how Automation Studio is very close to this is because of this field structure and this figure. Now these are the sources, hydraulics and pneumatics. They are your fluids, what we can say is here the control valve, and then the main actuator, which system is going to be actuated, they are actuator. This right hand system entire, generally these all studies are taken in mechanical engineering. Now when I say actuator needs to be moved, actuator needs to control, I mean these control parts are governed by this engineering side. Now for this simple solenoid circuit or simple solenoid valve to be operated, and this valve has to be programmed or to be controlled efficiently using the purpose what you had thought of while designing the mechatronics process. Now what all are those things? Why electrical engineering, electronics engineering, or FFC, microcontroller? Now a beautiful advantage of you people is that if electronics person knows about these actuators, control valves, hydraulics, pneumatics, these concepts, I mean grabbing these concepts is not that difficult. With the Automation Studio, you can easily take these challenges very efficiently, and you already know this. You already know PLCs, you know electrical systems, microcontroller, you already have studied in electronics. What you need to learn is a bit about this mechanical system. Vice versa, in mechanical, for mechanical engineers, he knows pumps, he knows compressor, he knows control valves, he knows actuators, double acting cylinders, single acting cylinders, small knowledge of signal sensors. Now what he needs to do is that he has to learn a bit about programming side or controlling side. So both this put together becomes mechatronics and automation engineer. So it is that simple. I mean, if you see today's scenarios, today's demand of jobs, this is what they are looking at. Individually, if you come and learn Automation Studio, you can grab the expertise on both this electronics and mechanical systems. So this is a key platform. This is a very good canvas for all you people to learn both these systems at integrated level, so that you can escalate to the level of expectations of mechatronics and automation industry. We have seen there is a surge, there is a demand of so many industries, so many companies in defense. Now, there is a simple example I'm going to show you. In today's life, many of such companies has come ahead and developed such kind of applications. This is all-in-one COVID prevention kiosk. You can see automatic door opening systems. Wherever you go nowadays, wherever your physical touch is not required, you can take the advantage of this mechatronics and automation applications and develop your own instruments, develop your own processes. Mechatronics is going to play a very key role in the future, and you need to be equipped as a faculty. You have to show them that how Automation Studio is going to give them a canvas in which they can put their own ideas. Let's then process, let's be in the maintenance, wherever they want to go, wherever they want to see that they want to explore their ideas in simulation. Automation Studio is going to help them. So particularly, this is where Automation Studio is going to play a key role. Being said, I mean, you can create a digital twins of your mechatronic systems. How it is going to be done, that will be explained by Mr. Praveen Bell. And then how do you troubleshoot, how do you design, right from hydraulics, pneumatics, their key elements, their key components, how can you make a replica of your trainers, pneumatic trainers, then sensors on them, and then entire bottling plant. If you want to see, if you want to develop a small PLC operated systems, you want to develop a small automatic door garage systems, then traffic light signal systems, then you have so many applications which you want to make a digital twin in the software in a computerized environment. It will become very easy for you to develop this, and this is how simulation and Automation Studio is going to help you out. Now I'll ask Mr. Praveen Bell to go into the detail of this and help you to give you the flavor of how these all systems can be built. You will have a flavor of as if you are going to develop these systems. And with Automation Studio, I mean, it has become so simple that there are 18 modules have come together to your help. And with this, you can build this automation and mechatronic systems. We are going to give a focus on some electrical parts also, mechanical, then electronics, and how rigid systems can be developed at your place, sitting at your own desk. You can even monitor the performance of your students. You can give them lectures, you can take their practicals, you can give them experiments, and you can monitor their performance sitting at your own places. So we have a bunch of assignments also from SPPU, from various universities across the India, and we can tell them how to help and how to solve them. So with this, I'll request Mr. Praveen Bell to take the session and take the charge ahead. Thank you. Thank you very much.
Hello, good morning. This is Praveen Bell. I'll be taking you through the session on Automation Studio. And let me just share my screen. Can everybody? Hello? Can I?
Yes, sir. Yes.
Okay. So this session, there's a lot to show. I think we are around an hour and a half left. So I'll try to cover as much as possible. There are a lot of technology, a lot of areas, and I'll just want to show one or two slides. I don't want to waste too much time on boring PPT slides. So I'll take you through the software, what is happening, what are the backbones for IoT used, etc. There are a lot of things to show today. So basically, I'll just like to explain this slide in short. That in Automation Studio, we have something known as hydraulics and proportional hydraulics. Now, hydraulics we are all aware of. I'm assuming that all you professors are teaching subjects of hydraulic, pneumatics, and mechatronics, because typically the professors are the same mapping of professors. So hydraulics and proportional hydraulics. Proportional is an area where you use analog control of hydraulic devices such as JCB machines, where you have joysticks, pedals, foot pedals, proportional control, PID feedback controls. So Automation Studio handles all that. Then we have similar in pneumatics also. I'm quickly running through the slide because I want to go to the working copy. Then we have something known as fluid power component sizing. Now, typically we are aware of all the syllabuses across the country. We study them all the time, all the universities, let it be Anna University, Pune, Diploma, Karnataka, VTU, Gujarat. And we see that design as a concept in industrial fluid power is very wrongly interpreted. We typically use a textbook like Anthony Esposito. We teach some basic hydraulic pneumatic theories and calculations, but when it comes to practical implementation on real hydraulic pneumatic kits or experiments, design is forgotten. We create certain things which move and we consider this as design. It could be piston synchronization, or it could be piston sequencing circuits, whatever, meter in, meter out, but we really don't do any type of a design condition. So this fluid power component sizing is specifically meant for design based circuits, in which, for example, you can have a piston at an angle of 45 degrees carrying a load of 1.5 tons, and I need to extract this in exactly 2.5 seconds. How do I achieve such type of conditions? So this design is very important and widely used by industry. Then we have something known as mechanisms and mechanical linkages, in which you can do real life loading conditions. For example, a particular hydraulic cylinder is doing work. It could be a series of cylinders on maybe a excavator arm, which has got 5-6 degrees of freedom, and there are loading conditions on this entire assembly. So how do these linkages behave? I'll be showing you examples of all of these. Then we have troubleshooting and diagnostics, where you can introduce faults in circuits. You can jam particular pistons, cylinders, etc., and you can tell the students how to troubleshoot these particular circuits. Then if you see the red section, this entire red section is controls. So we have electrical controls, JIC, IC. So depending on which textbook you are following, typically it's Anthony Esposito, Bolton, or it could be Mujumdar. These type of textbooks for hydraulic and mechatronics, and they typically use a JIC electrical symbol library. If you're following anything American, yes, we have that electrical library also. Then in the PLC ladder diagrams, we have different types of PLCs, Allen Bradley, Siemens, IC. There's a fourth one introduced, LSIS PLCs. And in the upcoming version, we are including Mitsubishi also. So you are at a freedom to use any of these PLC ladder logics. Anyone doing PLC programming will know that if you are using Allen Bradley and Siemens, a lot of components are quite different, except for the NONC contacts. For example, Allen Bradley PLC timer will have a EN and DN bit to actuate the timer, whereas Siemens T-on, T-off delay timers do not work like the Allen Bradley. They have a different logic of working. Then we also have sequential function charts. Now in the industry, 60 to 70% of work is actually happening in SFC in PLC programming. SFC is a programming language for PLCs. And in the industry, it is very strong today. Ladder programming is slowly becoming defunct. And I'll be showing examples of this. Then we have digital electronics, AND gates, OR gates, SRJK, D flip-flops, experiments like De Morgan's theorem, etc. Those can be done. Then we have HMI and control panels, where you can build different types of control panels, dials, gauges, buzzer alarms, etc. We also have 3D, in which you can import 3D parts from other 3D modeling software, create an entire assembly, and link it to hydraulic pneumatic circuits. We also have a full-fledged electrical module in Automation Studio, but that is not the scope of today's lecture because we are mechanical engineers. But we have things like three-phase motors, alternators, generators, synchronous, asynchronous, motor design control. And these electrical circuits can also be linked to the motors of the hydraulic system. For example, a motor is driving a particular hydraulic pump. You can interface electrical and mechanical also in Automation Studio. Then we have something known as manufacturers catalogs. Now this is very strong in the industry because what we see in textbooks today, we teach a pump is a round symbol with the arrow. But go to Bosch catalog and pick up a pump is the entire manifold assembly in which there are different types of ports, failure devices inside, a lot of things which go in one particular pump design or any type of a manifold. I'll be showing you industry catalogs. It will be more clearer then. but we have more than 50,000 components in industry catalogs by the catalog number: Bosch, Rexroth, Eaton, Danfoss, Hydrafoss, but they are not available for education as of now. They're only in the professional version, but you need to understand companies are doing professionally. Then for communication, we have a very strong technology known as OPC client. The world today is using OPC for IoT based implementation. A lot of factories are using OPC as the backbone for communication between their machines, their software, the cloud, and OPC has to be understood. I'll be showing you OPC also in this particular session. Now, partial users of Automation Studio are, you can see it's a long list: Komatsu, Eaton, ABB, John Deere, etc. I don't want to get into details of this, but there's a long list of users. We have a special web licensing concept for this COVID times, because students cannot attend the lab. Some student is sitting in Delhi, someone in Karnataka, someone somewhere else. So we have an option now that the students can load the software on their local laptops anywhere in the country or abroad. And there is a WW license. So when he logs on, he's asked for a username, passwords, which connects to the Canadian server, and he's allotted a particular license. So we are promoting this very strongly in these COVID times. So this is also available. So let me go straight to the working copy of Automation Studio. If you can see my screen now. Now this is a very, very strong simulation engine, and it has evolved more than 25 years, more than 5,000 components in Automation Studio. And I'll be building only one circuit. Rest I've got examples ready to show you. Now, what makes a good simulation software? A good simulation software needs to take into consideration a lot of real life problems. Yes, yes, sir. Someone was saying something. Can I continue?
Yes, continue, sir. Yes, continue.
Yeah, okay.
It was a disturbance.
Yeah. So if you see in the background, we have things like how accurate do you want your simulation? You want it at 0.1 milliseconds, you want it 0.5, you want 10 milliseconds, you can set the accuracy. You have things like force of gravity. Why is this important? Because a cylinder which is horizontal and a cylinder which is at angular position of, let's say, 90 degrees, the load handling capacities and the pressure buildup are very, very different. So gravity is very important during simulation. And we have things like thermal evolution. For example, a fluid is at 25 degrees in the reservoir, but the ambient temperature outside is 60 degrees. It could be a foundry. And how does this affect the viscosity properties of these fluids and piston extraction times, etc. So this plays an effect in simulation. Even things like cavitation, for example, the air percentage in the fluids, they start globalizing and they cause certain losses. Those are taken care of in Automation Studio. Another thing is that if you see the fluid manager, we have hundreds of ISO fluids available in the software. If you see here, these are all fluids used in the market, Tellus, Sunvis, etc. There's an entire list of fluids and their fluid properties. What is the viscosity of these fluids at what temperature? What is the bulk modulus? What is the bulk pressures? All these technical properties of these fluids are available. So before building a circuit, you can actually go and set these properties. Now, this may not be used in undergraduate, but anyone doing projects or MTech level, yes, all these properties are there in the background. Initially, pneumatics was considered as air, but now there are different gases which are now used in the industry. For example, butane, carbon dioxide, helium, hydrogen, oxygen, nitrogen, methane, propane. So, and the compressibility factors of these particular gases while doing simulations. Automation Studio understands the compressibility of these gases and what are the volumes which are in the lines and the components here. So these gas properties are there. We have things like materials, iron, steel, brass, copper. What is the internal roughness of these pipes? Is it rusted from inside? If there are T and elbow fittings, what are the pressure losses there, etc. So these are all the properties in the background. So building a circuit is very easy. I'll be building only one circuit online. I don't want to waste too much time in trying to build circuits here. I've kept a lot of them ready. So we drag and drop. 1 minute, let me just expand this here. So I'll be taking a few components and building a simple piston extraction circuit here. So I join these components. I just join the red dots. In a matter of seconds, I build a simple piston extraction circuit. Okay. Now, though this circuit looks very simple, there are a lot of conditions we as engineers cannot imagine what happens in a simple circuit like this. Now, before we explain such conditions, I'd like to show you certain things. Like, let's say I go to the pump. There are different models of this pump. Do you want an ideal pump? Do you want a pump based on head loss performance curves? For example, when we buy a pump from the market, we have these typical specification sheets which come with this. Yes, sir.
Sorry to disturb. Actually, the screen is still showing PPT. So if you are doing anything on the software, so yeah, that is not visible.
Okay, 1 minute.
Yeah. Share the screen of the software so that.
Is it seen now?
Just a second. Yeah, it is visible now.
Okay.
The software screen.
So, yeah, can you see the circuit now?
Yes, we can see now.
Okay. Is there a way to share the entire 1 minute? Okay, take it. You can see this. So now before I simulate the circuit, for example, okay, can you see this black curve screen? I'm just checking.
Yes.
Yes, sir.
Okay. Yeah. Okay. So in this particular, these are the head loss curves of pumps. So if you buy a pump from the market, they come typically with these curves, and you can set these curves manually in the software. Also, for example, if you click on the cylinder and you go to the data, you have the different properties of this particular cylinder. For example, what is the angular inclination of this cylinder? Is there an external mass on this piston rod? Is there a damping spring? For example, you can customize this entire cylinder. You can put springs, you can put brakes, you can put carriages. There are a lot of things you can do with this cylinder. This cylinder also has sensors mounted on it. If you want analog position sensors, you want speed sensors, you want force sensors, there's a lot of customization allowed on this particular cylinder. Also, if you go to the valve and go to the data technical specifications of this valve, you can see I can customize this entire valve. If I double click on the spool, let this open up. Yeah. If I double click on the spool, there are hundreds of spools available in Automation Studio. So I can customize, I can make a 7x3 valve of my choice, my type of spool positions. Internally, there are flow curves. We teach students flow curves of how the valves operate internally. So opening versus flow. So in Automation Studio, port to port specification of flow curves is possible from A to B, B to T, T to P. You can actually modify each and every curve here. Besides that, internal pressure drops, are there leakages in this particular valve? All these can be set internally. Now, simulation is very easy. I click on the simulation button and I can see this software is now simulating. Now, like I was telling you, there are certain conditions which we can't imagine, even being engineers. For example, let's say I go to my cracking pressure of my pressure relief valve and I make it 0. And if I ask a question, what will happen? 99% of the audience will tell me that the piston will not move. But in real life, that is not true. Even though the cracking pressure is set to 0, because the fluid is still passing through the system, going to the cylinder, hitting the piston disc, and then creating a back pressure. So this is what happens in real life. But now if I add a particular load on the piston rod, maybe it will not move because of the resistance. So such type of conditions this software internally understands. Now, while simulation is going on, there are certain components which are red in color and they have cross-section animations associated with this. So as a teaching tool, it becomes very, very handy for teachers to show the internal working of these particular components. So this is possible. Then we have an entire list of measuring instruments, flow meters, etc., pressure meters, etc. But more than that, what I want to show you is certain dynamic measuring instruments which Automation Studio carries. These are like probes. You take a probe and point at any point in the circuit. For example, I click on the cylinder and I drag. It automatically detects what can I measure for that particular cylinder. Linear position, speed, output position, piston side flow. It automatically detects what can I measure for that particular component. Or for example, if I point at a particular node, it automatically detects that at this point I can measure pressure, temperature, and viscosity. Or if I put a probe across 2 points, 1 minute. Do that. If I put a probe across 2 points like this, it automatically detects differential pressure. And now if I simulate my particular circuit, you can see the readings on all my measuring instruments here. Okay, so these are dynamic measuring instruments, but what we are more interested are in the plots and waveforms, because in the journals ultimately this is what we need to plot. So Automation Studio has the 3 types of plotters. We have Y as a function of plotter. We can have 2 such plotters at a time. We have Y as a function of X plotter, in which you can plot parameters versus each other. We have a Y, X, and Z plotter, in which I can have 3 parameters versus each other. 3 types of plotters are available. So I drag a component, put it on screen. I say I want to plot linear position, and I plot this particular form of piston position here. I stop the simulation, and I can put measuring points on this. So I can put measuring bars.
Sir,
I can measure the delta. Screen is not visible?
Yes, sir. Sir, previous
Sir, your
screen is
visible, but it is freeze. That's the
previous
problem.
screen is visible only.
Speed. One.
Only
Just
circuit
try
is
to
visible,
check
sir.
this one.
Yeah. It is only showing this. Sir, earlier you explained the piston mechanism. That screen is showing only.
Can you see this now? Is there a plotter seen on screen? What can you see now?
Not yet.
Not yet,
So
sir.
Not
it
yet.
will
Not
take
there,
time
1
to
minute.
load, sir. Just a minute.
Okay, what is happening now?
So it's blank.
Okay, what is visible?
Not yet, sir.
No.
Suraj ko सांग ना कसं Still blank?
Yes, sir. Still blank.
Okay.
Yes, sir. Now it's visible.
It's visible.
What can you
Circuit
see?
with
Can
the
you see a
project.
black plotter?
Yeah, project plotter
See a black plotter?
and circuit. Yeah.
You can see the plotter?
Yes,
Yes, sir.
Yes, sir.
Okay.
It is moving. Yeah, we can see.
Yeah, it is moving. Nah? Okay, I think we got connected. So this is the plotter screen, and you can right click on this plot. You can copy this plotter image. You can put it in your Microsoft Word. You can put it in PowerPoint, and you can zoom in, out. You can move the axis up and down. It's a very, very flexible plotter. You can even lock this particular plot, open a second. Yes, sir.
How we draw this, sir?
Yeah, I'll show you
Can
how
you
to do
explain?
this. Yeah, I'll just explain the process. I'll delete the previous plot 1 minute. What you do is you drag a particular component and just drop it on the 1 minute. You drag a particular component and you put it on the plotter screen. The moment you do that, the software automatically detects what can I measure for that particular component. So I drop the cylinder onto the plotter screen. It says acceleration, linear position, speed, etc. So I choose linear position. I say OK. And now if I simulate my circuit, you can see the plot. Can you see this?
Yes, sir.
Okay. Then we can put measuring bars. Let's say I put 2 measuring bars here, and I can measure the delta difference between 0 and the full position. So it's very easy. I just drag a component, put it on the plotter screen. For the pump, I say I need to check input flow. I resimulate the circuit. It will plot flow and piston position together. It's just a drag drop option here. You can export these values. You can plot, print them out, etc. So this was a very simple circuit here. I need to show you more better things now. So what we are going to move ahead is actual, let's say some basic things, but where engineering is involved, and that is sizing sheets. That this is where you do design-based circuits. Now in our syllabuses, we typically teach students things like 1 minute. Let me just open this 1 minute. 1 minute. I'll just open this. In a wrong circuit. Okay. Now in sizing sheets, we tell students to build circuits which is maybe pistons in series, pistons in parallel, and we are over with the practical, but they really don't know the difference between what is the behavior of these particular components. So what I'll do here is that I'll take a simple circuit where there are 2 pistons in parallel, then 2 pistons in series, and let's see their behavior from an engineering point of view. So let's say I take parallel cylinders here. Okay, I take parallel cylinders, I open a plotter. I want to plot the piston extractions of both these particular pistons. Screen has gone blank.
It is blank.
Yeah, it just went blank. I'm sharing it again. Even the mobiles. Is it visible again?
Yes, sir.
Yes, sir.
Okay. Sorry about that. I don't know why this is happening. Visible now? Is it visible?
Yes, sir. Yes, sir.
Yes,
It's
sir.
visible.
Yes, sir.
Yes.
Okay, sorry. So now, before the parallel example, I'll just show you one simple design-based situation. For example, I have this particular piston, and I want this piston to extract in a particular time frame. Okay. For example, I want this to extract in maybe exactly 3 seconds or something like that. So this is a circuit which I built, and we have not designed it. There's a random extraction time. Okay. So first, what do? We go to the pump, and in the pump, we'll note down the piston rated flow. So in the piston, the flow I'm getting from this pump is 120 liters per minute. I note down this particular value. Okay, that is the flow coming from the pump. Then I go to the piston, and here I have this sizing sheet module in Automation Studio. Now this is what the industry uses very, very strongly, because all the designing happens here. You see here in Automation Studio, there are hundreds of equations available. Okay, and each of these equations has got a solver at the bottom here. Okay, so in these equations, there are certain values which you know, and there are certain values which you don't know. Okay, I'll just expand this. Okay, so if you see the section on the left hand side bottom where my mouse is, there's an input section and there's an output section. For example, in a circuit, we know that the pump is giving me 120 liters per minute. I know that I need a piston extraction time of 3 seconds. What I don't know is maybe the diameter of that piston for a particular stroke. So what I do is I pick up a particular equation in which on the input side, I have time as an input. I say I want the extension time of 2 seconds. Okay, piston diameter, let's say I put it as 50 mm. Piston side flow, this flow is coming from the pump. I put this as 120 liters per minute. The moment I enter these values, the software automatically calculates the stroke of the regular cylinder. So the software tells me that for this piston diameter, extend time of 2 seconds and a flow of 120 liters per minute, the stroke of the piston should be 271576. 1 minute. The stroke length I need. I pass this value to the particular cylinder. I say OK, and now I plot my graph again. Again, minute. I'll simulate my circuit again. I simulated my circuit, and now if I measure the piston extraction time, the extraction time here will show me the value which I have put, that is 3 seconds. So in this way, I can do sizing of my particular components. Now, I want to show you something very interesting. Let's say I take 2 particular pistons like this, and I want to connect them in parallel.
Sir, it's again.
It's gone again?
Excuse me.
No, it's visible now. Yeah.
Not visible?
No, sir. It's okay, sir.
Okay? Yeah.
Yes.
Okay. Okay. Now, I want to show you a particular condition here. I've taken 2 cylinders in parallel, and I'm going to simulate this particular circuit here. The moment I simulate, you can see that these 2 cylinders have moved in synchronization. Even the 2 plots here, you can see the cylinders, they have extracted tightly in coordination. If you see the 2 graphs, they exactly match. So we think that piston synchronization has been achieved in parallel. But now if I go to the second cylinder, and I go to the second cylinder and I say give it an inclination of maybe 90 degrees, and I simulate the circuit again, you'll see that total synchronization of these 2 cylinders has been lost. There's a total loss of synchronization here. So I'd like to point out to this particular section of the graph here. So if you see the yellow cylinder, this was not at an inclination. So it went smoothly right to the end and to the end position. The other cylinder, which was at 90 degrees, slowed down. And if you see at this particular point here, I'll put a marker here. At this point, the first cylinder has already reached end position. At this point, the extra fluid comes back to the second cylinder and increases the acceleration of the cylinder, and it shoots up in its speed here. So such type of behaviors you can actually see in a simulation software. Now this cannot be explained on a trainer kit. So such type of conditions here. So you can do this. Now if I add another load on this particular cylinder and let's say make it external mass of 1000 kgs, again there'll be a different behavior. So in this way you can create very, very interesting practicals which are based on simple theories, cylinders in series and cylinders in parallel. Now what happens in series condition? Now in series condition there's another problem. See, these are very basic circuits which we teach, but we never got to teach the students in this particular fashion. Now in this particular circuit, I put them in series. Okay. I take the first cylinder as a linear position, second cylinder linear position. I simulate this particular circuit. And what happens in this case is something different. We see that the second cylinder does not reach the end position. That is because the piston side, the rod side volume of the first cylinder is not enough to give that much of volume to the piston side of the second cylinder. Those two cylinders are identical to each other. So the second cylinder never reaches the end position because there's a volume difference because of the rod being present. So how do you solve such a problem? What I do in Automation Studio, I go to the first cylinder and I note down the rod side volume. Rod side volume says 2945 centimeter cube here. 2945 cubic centimeter. 2945. We note this down. I go to my second cylinder. I go to sizing sheet. Okay. And in my sizing sheet, I can create a new sizing sheet. I can say that I know the piston side volume, which is the rod side volume of the previous cylinder. So piston side volume, where is it? Let me check. Piston side volume as an input. I know the stroke. I want the software to calculate the piston diameter. Where is diameter? 1 minute. I know the stroke. I know the piston side volume, and I need to know the D. Piston diameter. Okay. So when I chose these values, I know two values. I know the stroke of the second cylinder. I know the piston side volume, which is 2945, which is the rod side volume of the previous cylinder. And I want the software to automatically calculate the piston diameter. So I go to the piston side volume and I put in the value of 2945. 2945. I put a stroke of 500 mm. Software automatically calculates the piston diameter. I pass that value to the cylinder. The cylinder is sized. Now if I simulate my particular circuit, you'll see the pistons are totally coordinated with each other. Both of them moved. The second piston reached the end position. And you see in the graph also, these are the piston extractions of both the pistons here. So such type of sizing and designing can be done. So you can do a design of maybe a cylinder at an inclination carrying a load of 2 tons and I need a velocity of a particular value. I can do such complex calculations also in Automation Studio. So this was how to design circuits. Then coming to putting loads on actuators. What happens is we teach students different type of circuits theoretically, but how do they actually behave when we put certain loading conditions? So Automation Studio has two types of loading conditions on pistons. One is a driving force curve and one is a resistive force curve. In a driving force curve, I'll just take a small example. Now here in this circuit, this is a circuit of a hydraulic pump which does not have a electrical pump or anything. When a car gets punctured and you put this hydraulic pump under your car and with your hand you're operating a particular lever. So there's no external power supply. So how do I tell a particular piston that I'm applying a physical force to you? So I double click on this cylinder here and I come to force curves. And I have a driving force curve here. So for minus F and plus F, I put two opposite forces. Okay. And if I simulate my circuit, you'll see the piston on the left hand side automatically starts moving because it is like holding the piston rod with your hand and pumping it up and down. So this is a driving force curve. Now this is a driving force curve, but what about the opposing force curves? For example, let's say a piston is mounted on an excavator and this excavator is pushing sand. So as the piston moves out, the sand which piles up starts increasing. So the opposing force also increase. So I double click on my cylinder, I go to resistive force curve, and you see here I can decide the opposing force which is being applied to my particular piston rod here. And as an engineer, I want to measure the pressure which is built up inside my piston here. So I'm plotting the pressure as well as the linear position of my particular piston. So I simulate the circuit, I operate this, and I'm going to pause my simulation here because there are certain interesting things which have happened here. Number one is that the blue curve which you see is the pressure buildup on my piston side. Okay. And if you see on the circuit, the piston does not reach 100% extraction. It stops around 75 to 80%. This is because the external applied force is so high that the piston just cannot push anymore beyond this particular point, and it stops there. Plus there is a spike in the system, and this spikes could be very dangerous. It could burst hose pipes, etc. So as an engineer, what do I do? Then maybe I can put an accumulator in the circuit so that it can absorb a portion of the spike. It can give me extra flow. So then you start building around this circuit. But on this circuit, what I'll do is, I'll do something very simple. I'll start the simulation and I'll change the cracking pressure. I'll increase the pressure of my pressure relief valve. And here I noticed that at a particular pressure relief valve setting, the piston extracted fully here. So these are types of design which you can do in Automation Studio. You can build on this circuit, refine it like what an engineer would do actually in the industry. Is it clear so far?
Yes, sir.
Everything okay?
Yes.
Okay. Okay, now another interesting feature which we have, we are going to be moving to mechatronics very soon. So we will be coming to PLCs, electrical controls, but just one or two few of these circuits I need to show you before that. In Automation Studio, we also have troubleshooting. Now, what is troubleshooting? Let's go to pressure relief valve. On the left side, I have an option of introducing faults in the particular circuit. So for a pressure relief valve, I can introduce faults such as faulty opening, cannot reseat properly, always fully open. So I can take a particular failure and I can introduce the failure for a particular condition also. That when the system reaches maximum flow, I want this component to fail. And then I want the students to go and troubleshoot this particular circuit, because we've seen in certain syllabuses, create an experiment for troubleshooting, but nobody knows how to address this particular problem. So how do we do it in Automation Studio? Okay. Now I have a basic circuit here. I simulate this circuit and piston is extracting, it is retracting, not a problem. Now what I'll do is I go to the piston and I jam this particular piston here. I say jam, failure actuated. I say okay. Now if I try to simulate my circuit, you can see the piston is not extracting because the circuit is jammed. So what do? I take a hydraulic tester. Now this hydraulic tester is similar to the tester which these engineers carry on field, John Deere, Caterpillar, and I connect the two ports of my tester here. Okay. And when I connect this, I can see that there's a problem in this particular system here. So what do? I come to a repair tool. I click on this particular cylinder. I select the failure, select the jam piston. I say clear out the failure and it starts moving now. So such type of troubleshooting options are also available in Automation Studio. You can declare a particular failure and then you can troubleshoot this particular circuit. So different type of devices are available for that. Then coming to thermal simulation, Automation Studio also has thermal simulation. We do not teach this in UG syllabuses, but this plays an important role in people who are doing actual real life simulations. Now in this circuit, there's a pump which is pumping fluid at 25 degrees Celsius. And we have put an orifice in this particular circuit. And this orifice, because of the pressure differences on both sides, is going to cause a temperature rise on the other side. So if I simulate this particular circuit, you'll see because of this orifice opening here, 25 degrees fluid is heating to 30.7 degrees Celsius here. So now what do? I can't send this liquid, the heated liquid, back to my entire system. I need to cool down this liquid. So what I do is I divert the liquid to the left hand side of the circuit here. And in this circuit, I put a cooler here. I can set the efficiency of this cooler. There are a lot of settings in this cooler. I can cool this liquid back. Here it is cooling it to 28 degrees Celsius and sending it back to my reservoir. So such type of thermal simulation can also happen in Automation Studio. Typically in UG syllabuses, we don't address thermal conditions, but yes, the software allows you to simulate this. Then coming to electro-hydraulic electro-pneumatics. Now we are entering the area of controls and the mechatronics side of Automation Studio. We have a large list of sensors in Automation Studio. Position sensors, mechanical sensors, proximity sensors, etc. And in this particular circuit, what I've done is, on this cylinder, I mounted two sensors, SEN01 and SEN02 at 0 and end position. And these sensors give out signal to this particular electrical circuit here. So there are two sensor switches. There are two solenoid coils which are attached to this particular hydraulic circuit here. Now, if I simulate this particular circuit, you can see that the sensors are triggering, they're operating the electrical circuits and the solenoids, and it goes into a self-reciprocating action here. Now, because this software is of a fluid power background, I can maybe change the displacement of my pump. You can see it is moving slowly now. It will respond accordingly. I make the flow high, it moves faster here. So, using this electro library here, this is a JIC electrical library. You can build any type of electrical circuits. You can pick up any textbooks. There are thousands of components, all types of components. It could be a batching process. One cylinder triggers the second, triggers the third cylinder, then all of them return together. Different types of logics you can build in electro-hydraulics, electro-pneumatics. The facility is available here. That was electro-hydraulics. Now, as far as college circuits go, there are hundreds of college circuits, and we've seen right from diploma to even IITs. Typically, they teach the same thing, basics of fluid power. Then you have meter in circuit, meter out circuit, pump loaded, loading, unloading, series, counterbalance, etc., etc. There are hundreds of circuits available. And the best part about Automation Studio is that Automation Studio has tied up with Anthony Esposito. Anthony Esposito is considered the Bible for fluid power the world over and in India also. And chapter number 18 now in Anthony Esposito's Automation Studio. Not only that, the entire college circuits, there must be hundreds of circuits in this textbook. They are available free for download from the website of Automation Studio. So teachers don't even have to build these particular circuits. These are all ready for download. You can see chapter 3 circuits are available. Chapter 9 circuits are available. All these circuits are available for free download. So I'm not going to explain the circuits. Any circuit is possible. But I want to show you the advantage of how can you conduct a practical in a better fashion. Let's take a simple circuit of a study of accumulator. We teach students this, but they never get to perform a practical on this and take measurements. So in this particular circuit, there are two circuits which are identical to each other. The left-hand side circuit has an accumulator. The right-hand circuit does not have an accumulator. And we want to see the effect of the accumulator on this particular circuit. So we simulate the circuit and you can see that the accumulator is charging here. You have to give it time to charge. Once the accumulator is charged, we'll operate the cylinder without the accumulator and then the cylinder with the accumulator. I'll stop the simulation. If you see the graph here now, you can see that the piston without the accumulator took longer time to extract. The piston with the accumulator, there's a very sharp extraction time here. You can now measure these values. You can see the effect of an accumulator here. You can change the parameters of the accumulator also. You can size the accumulator according to your requirements. Later on, I'll show you an interesting example of a defense project in which there were 3 accumulators which were supposed to do a particular cycle 3 times if the electricity fails. I'll show you some case studies. So you can perform practicals in a much better way which make more sense to students and put them in your journals. So that was study of accumulator. Now we are coming to an area of hydraulics pneumatics which is proportional hydraulics and pneumatics. Now this is where we are getting into a little advanced category of circuit design. Before that, I want to just explain a few things in proportional. Okay. Okay. Now, in proportional hydraulics, a large part of the industry uses proportional hydraulics, and this is very ignored in the educational sector here. In SPPU, I think the last, not this current syllabus, in the last syllabus has introduced PID controls and proportional hydraulics. Again, it was removed. Teacher didn't know how to conduct this particular. Can you see the screen? Can you see the PPT?
Yes, sir.
Yes, sir. Yes, sir.
PPT, no.
The PPT, this one?
Yes, yes.
Yes.
PPT is seen, right? Okay.
Yes.
No, sir.
Yeah.
But PPT is not
And
showing
proportional hydraulics.
software.
It is still showing software?
PPT is not visible.
Yes, sir.
Okay. Maybe I need to share that. Because in Microsoft Team, it asked me to share which particular screen. Okay. Now I think it should come on.
Yes, sir. PPT is showing now.
Yes?
Yes, it is now. Now it's.
Okay. So proportional hydraulics in the industry is a very important role, because see, things like electro-hydraulics, electro-pneumatics, these are logical controls. It's like on-off. You know, the automation plant, bottle filling, cut, they're just operating. But when it comes to things like JCB machines, earth moving equipment, these all require proportional control. So all these earth moving companies, agri, aerospace, they all require proportional hydraulics. And if any of the audience is part of Board of Studies, please get this into the syllabus. It's a very important section. Anthony Esposito also has a large thing on proportional hydraulics. This should be part of syllabus. So if you see in the JCB machine here, there are things like the operator has got a foot pedal, he's got a joystick in his hand, and these controls are used to operate these arms here. Okay. So the components also which are there for proportional and hydraulic, this particular area are very different. Here you need to study PID controllers, you need joysticks, foot pedals, analog devices. Even the valves and valve cylinders are a different category of components in proportional. So now, if you can see this basic chart here, the first column is directional control valves. And now these are typically 99% of the colleges have only these. And these are known as on-off valves. So typically when you buy a hydraulic pneumatic trainer kit, you have it in your lab and you just operate it as an on-off type of a valve. Okay. And you do your practical. Now the second category is the proportional valves. In proportional valves, if you see the symbol of the proportional valve, on the solenoid there's an arrow. And this arrow indicates that I can attach an analog signal to this particular valve here. I can control the position of the spool accurately. Okay. And in the servo valves, if you see the valve, there is a servo motor mounted on that. So in proportional valves, it's a solenoid operated valve with analog control. In servo valves, there's a proportional servo motor which moves and has more accuracy on the particular valve. Okay. So this one particular slide, let me zoom. I want to show you certain things here. Okay. Now this particular slide, if you see here on the left hand side, if you can see my mouse, there are these internal flow channels, and there's a spool. And if you see this, there's an overlapping area here between this spool body and the channels inside. And if you see, there's an overlap here. Okay. And on the right hand, so the left hand side, this is a proportional valve. This overlap is very high. If you see in the servo valve on the right hand side, if you see the overlap, it is almost zero here. It is that accurate here. Okay. So how does this affect? So we'll see in this particular slide here. Okay. In this particular slide, if you see, when the valve is opening and the flow is coming out, there is a dead band here. And this dead band decides how accurate your particular valve is. So if this dead band is 3% or more, it comes in the proportional valve category. And if this dead band at the center is 1% or less, it comes in the servo valve category. That's why servo valves are very, very expensive in the market today. So a small video on how a proportional valve operates, and then we'll see a servo valve also. These are short videos, hardly 20-30 seconds. Because this is used everywhere in the industry. Let it be aerospace, let it be earth moving, any of these big machines, they all require proportional hydraulics. Okay, so this is how a servo valve operates. A proportional valve operates. And if you see a servo valve, it is very, very different. There's a servo motor mounted on top. There's a leaf spring which gives a feedback back to the motor, and it's a very, very accurate sort of a control. It is also an interesting subject too. If you get this in the syllabus, study of proportional servo valves and feedback control hydraulic systems. You can actually have 2 or 3 experiments in the syllabus also. In fact, a few MSME tool rooms who are using Automation Studio, for example, CITD, Hyderabad, etc., are teaching a lot of this technology. So this is how a servo valve operates. Okay. And we'll come to feedback systems a little later. First, let's see how Automation Studio behaves. So let me share my software screen again. Can you see my software screen now? Software screen is visible?
Not yet, sir.
No, sir.
It will take time to load. Wait.
I'm waiting. So is there any way to share the whole screen instead of applications? Because I'm using Teams for the first. Is it visible now?
No, sir. It is not visible. No, sir.
Is it visible? Is it visible?
No, sir.
No, sir.
Not yet. You see it?
No, sir.
No, sir.
I've shared it second or third time now. So, what is visible on your screen just now?
Software.
Software.
Software window.
Now it is visible, sir.
Achha, now it is visible. Okay, so what I'll try to do is I'll try to keep in the software only. I'll not shift between PPT and this thing now. Okay, that'll be better. So it'll less disturbance. So if you see in this particular circuit here, we have a valve here. This is a proportional valve. Automation Studio has an entire category of proportional and servo valves in the library. On this valve, you can see there's an arrow symbol here. This indicates you can attach an analog signal to this particular valve here. And to give a signal to this particular valve, we have steering wheel, joystick, foot pedal. You can attach different types of graphs. A lot of input analog devices here. So in this case, we have attached a joystick signal to this proportional valve here. And if I simulate this particular circuit and I operate the joystick, you can see that by moving the joystick, I can operate the piston position in an analog fashion. But now, there's something very bad which is happening in the circuit, and that is that if I move my joystick to the right, the cylinder runs in one direction. I have to play with my mouse to keep it stable in one particular position. And this is because this is not a feedback controlled circuit here. So there's a lot of error in the system, and that is why we have to devise proportional feedback systems. And proportional feedback systems, I'm not shifting to the PPT now, but I'll tell this verbally now, is that we teach students PID control systems in engineering. Let it be mechatronics, mechanical engineering, chemical engineering, instrumentation, production engineering. PID systems are taught to students. And typically in PID systems, what we do is, whoever is doing practicals in PID tuning typically will go to a software like MATLAB Simulink or LabVIEW, and in that particular software they'll make a small control system. They'll put a step wave input, and you'll check on the oscilloscope the behavior of the PID. So for a high value of P, let's say 800, you'll get oscillation. Then you cut this down. You do a sort of a PID tuning experiment. But that is very, very mathematical. I'll prove to you that how much more is actually required to do a real PID control. So now in this particular circuit which I'm showing you, what is happening here is, I'll explain this. We have a PID controller here. This is a PID controller. The piston which is here has got a sensor on this particular piston here. So there's a position sensor which is giving out a signal -10 to 10. This is an analog feedback signal. Then I have a joystick. Joystick is giving out a signal -10 to 10. These two signals are coming to the PID controller. PID controller is doing the error calculation and then sending the signal to the proportional valve. Okay. So if I simulate this particular circuit now, if you see, it came and stopped at mid position. This is because the signal is at 0. The joystick has a range of -10 to 10. Right now it is in 0 position. It's come to center position. So if I move my joystick to the right, you can see the piston is now accurately following my joystick position. And in the graph, I'm plotting the piston position versus the joystick position here. But now again, this is still not a good enough practical to put in the journals because my hand is shaking, the signal of my joystick is shaking a little bit, and I can't get accurate study plots like I would call them. So in this case, how do we do a real PID tuning experiment for mechatronics and industrial fluid power? So I'll give a very good example of that. In this case, now we'll use a graph and I'll show you how much different it is from how MATLAB and Simulink would behave. Okay. Now in this case, I have this circuit here. Piston position is given to the control device, and instead of a joystick, now I'm now giving a graph signal here. Okay. This is a graph signal, and you can see the graph has got a scale of -10 to +10. And my graph is not reaching the end position. I've kept a little gap at the bottom and at the top. So on the minus axis, it is around 9, and on the top, it is around 8. It is not 10 to 10. Okay. So that is a 9 to 10 graph. It is not -10 to 10 completely. I'll tell you why. Okay. There is a reason. I'll simulate this particular circuit. Initially, I'll go to my controller and I'll give a proportional gain of 8. I'll give an integral gain of 0 and a derivative gain of 0. Okay. So if you're teaching PID theory, typically you'll be teaching students Ziegler-Nichols method, manual tuning methods, etc. But generally they revolve around one concept, is that first give a p-value very high, DNI 00, and get a condition of ultimate oscillations. Once you get a condition of ultimate oscillations, then what do? Cut down the proportional gain to maybe half that value. So I'll make this 3.5. I put in an integral gain of 1 and I'll put a derivative gain of 0. And typically between minus 1 and 0, you attain fair bit PID control here. Okay. Now this is what you would see in MATLAB Simulink also. Now let's come to the interesting part of what happens in a real hydraulic system. I've set the PID gains again to 800. Okay, oscillations have started happening. Now what do? I go to the pump, and reduce the pump displacement. The moment I reduced my pump displacement, my oscillations went for a toss. Most of them were already gotten rid of. Now this is a condition which MATLAB Simulink will not show you. Because in a real hydraulic system, there is a pump displacement. There is a flow characteristics of the valves. There is a pressure relief valve, its pressure. There will be internal flow curves of the valve itself. Then there is damping springs if they are present on the cylinder. What is the cylinder flow characteristic? All these values are not, you cannot put them in a mathematical model in Simulink, or then you have to be a real scientist to think of all these conditions. Okay, right from viscosity properties of fluids, you start at that level. So in this way, if you see, I am now increasing the pump displacement again. Oscillations have started again. So now let's leave it at this value. I'll do another interesting thing. We are getting oscillations. I go to the graph, and this graph value I shifted to now, which was at -9 to +8. I shifted to -10 to 10 here. Okay. Bottom I'll not shift it to 10. I'll leave this at 8, and the top graph I've shifted it to 10. Now I simulate this particular circuit. You see something very different happening in the graph. Let me explain this to you. What is happening now? I got oscillations when the piston is hitting the negative side. When the piston is going to the top, there are no oscillations here. There are no oscillations here because the piston is hitting the wall of the cylinder. When the piston extracts, it goes and dampens against the wall of the cylinder. Now this is again a condition which you cannot think about in MATLAB Simulink, doing a PID tuning. So at the bottom, there is a place for the piston to oscillate. At the top, it is damping against the wall of the particular cylinder here at the top here. So there are a lot of these conditions here which give you a real life condition of a PID controlled hydraulic system here. So that is a way you can build a PID tuning practical for your students here. In fact, there are circuits with multiple PID controllers, master, slaves, etc., etc. Okay. Now let's come to another area. We also have 2D animation in Automation Studio. By using the drawing options in Automation Studio, you can create 2D animations. Now in this particular circuit, if you see on the left hand side, using the drawing options in Automation Studio, like what you do in AutoCAD, you can build an excavator arm, make joints and connect them to actual piston movements here. So such type of 2D animations are also possible in Automation Studio. There are certain student projects which were done in the last 2 to 3 years where students have built such type of animations also. I'll showcase some student projects in the end of this demo. So we have 2D animation. Then, okay. Now, I'm not switching to the PPTs. We are running out of time also. We have half an hour left. There's still a lot to show. Automation Studio also has a very, very large catalog library available. Now, what they have done is for the industry, for example, Eaton, Pimpri, Kharadi, Pune, they have an official tie with Automation Studio, and the entire Eaton libraries are available in Automation Studio, pump, cylinders, stack blocks, etc. And for the industry components, the catalog is slightly different here. For example, let's say there is this Danfoss is a company, okay, and in Danfoss, let's say I go to the PVG 120 category, okay, and here if I see there is a image of that particular component, the actual physical image, the layout of that particular component, the documents which are there. So if I click on this, I come to the specification sheet of that particular component here. Okay. So every component in the catalog manager is documented here by model number. The internal properties of those components are also fed into this particular components here. So if you say that I want to pick up a particular pump from Danfoss or Bosch Rexroth or any of these companies from the catalog and pull it and drop it on the screen, it will behave like that component which you buy from the market. So the companies, Danfoss, Eaton, their engineers sit with the engineers of Automation Studio. They sit together and they've developed these catalogs, and the behavioral characteristics are very, very similar to the real life components. So what are these catalog components? I'll give a simple example that what we teach in college and in the real life what happens. Okay, now let's say there is a circuit of a excavator machine in which there are 2 or 3 joints. So there are 2 or 3 cylinders which operate joints of freedom on this particular mechanical arm. So such type of circuits, there are ways of building it in catalogs in the industry. Let's say I want to build that particular control section by using Danfoss PVG proportional valves. PVG stands for proportional valve group, and PVG is a concept which is pretty popular. Danfoss has a PVG 3200, 120. Eaton has a parallel. They don't call it PVG category. They call it system stack valves. They cascade valves into each other. How does this work? Okay. So let's see. We have a basic module here of PVG 120. So if you see here, what I dragged onto screen is a manifold block. This is the casing of the PVG valve which you call, okay. This is the casing. I can pull out, let's say 2 casings here. I've pulled out 2 casings. I'll zoom at a particular section here. If you see at the bottom here, you can just drag these 2 casings and plug them into each other like this. And you can see that 2 casings have been cascaded into each other. Each of these casings are going to be responsible for one movement of an actuator. Okay, so I put in 2. Then let's say I want to put in a proportional valve. So I can choose the valve by model number. I can pull out a valve. I pull out a second valve. Okay. I'll just zoom into a particular area here. And if you see, this valve totally plugs into this particular casing here. If you see here, these are 2 blocks which have been cascaded into each other. So Danfoss makes these blocks, and now each of these blocks is responsible for a particular movement. So at the top here I can attach the cylinder here. 1 cylinder here, a second cylinder here, or it could be a motor. Then there's a pump side block also from where the fluid is coming in. So let's go to the pump side modules here. So if you see, there's a pump side module here. I plug it out here. This again cascades and fits into my block here. Then I want to introduce a section inside this. This again plugs into this. I build the pump side assembly here. So in this way, in the industry, you can cascade. That is why it is known as a proportional valve group, PVG. Each of these units is responsible for one piston movement here. So if there are 5 pistons, we need 5 such blocks. Now, how does this help is that if you're building a tractor circuit or an excavator circuit, what happens is you can't have 10 walls. You take a mount. How are you going to mount the entire thing under on the machine? You cannot have walls randomly connected, fitted with screws, nuts, bolts here and then. So they create these manifold blocks which are pluggable into each other, and in this way you can build on circuits here in Automation Studio. So this is the PVG concept of Automation Studio, how the industry behaves. Okay. So that was a catalog component. Now coming to another feature, which is mechanisms. Now mechanisms are a very advanced way of loading actuators in Automation Studio. We had 2 projects. One was from GCOE Amravati, and there was another project from another batch of students, I think MIT College. This was an old project. There were 2 projects. So one project was a cotton baling machine, the Amravati project. It was a UG 4th year student, mechanical. And they want, in the cotton baling machine, there were 2 or 3 pistons where the piston rods were welded together and they had to move together. Okay. So there was a plate which shorted all the piston rods together. And then the load on this particular assembly behaves in any particular fashion. So how do you simulate a condition like that? So this mechanism manager takes care of such type of situations. Now I'll explain this. It is very interesting. In this particular circuit, if you see, there are 2 circuits. On the left hand side, there's a pump, there's a valve, and there's a cylinder. But on the right hand side, there's just a cylinder attached to a reservoir. There is no pump assembly on the right hand side. But in real life, I've taken a metal rod and I've clamped the 2 cylinder rods together. Okay. Even people like Cummins or let's say ISM Dhanbad, they are building these rock breaking mechanisms, and they have these conditions where you have these multiple piston rods welded together, breaking rock. So these conditions are required, and this is where you build this mechanism for this particular condition here. The 2 piston rods welded together. There's a way of doing this. I'll show you how this behaves. Okay. Now, since the 2 rods are welded together, if I operate the circuit on the left hand side, it pulls out the piston on the right hand side. Okay, so this is a real life condition here. Now, I go to the second cylinder here and I jam the particular piston rod here. I say jam the piston rod, and now if I simulate, you'll see that the second piston cannot be pulled out because the second cylinder is jammed. Again, this is a real life condition. So I come to tools, I come to troubleshooting. I take a repair tool, I go to the second cylinder, I said select the fault and open the jammed piston. It now moves. So such type of mechanisms can be created in Automation Studio. It could be very complex. It could be a chain of pivot joints. It could be moving some bodies. You know, different types of mechanisms can be created in Automation Studio, and these will behave like real life loading conditions. This is the way actual loading should happen. Okay, then okay. We also have 3D in Automation Studio. In Automation Studio, we have our own Boolean modeling software, but it is not so powerful like SolidWorks, IDEA, CATIA, etc. But if you have parts created in 3D modeling software, You can import them by using the STL, IGS, DXF file formats, flat file formats, and get them into Automation Studio. So in this case, we have taken an arm and a bucket, and we have created a joint here. And this joint has been linked to the piston movement in a real hydraulic circuit here. And now if I simulate this particular circuit here, the piston will actually operate my 3D movement here. So such type of 3D interfacing option is also there in Automation Studio. But let me show you something more interesting. Let's say I have a hydraulic circuit, I have a industry steering block, I have a mechanism manager, and I have 3D. I want all of them to work together. So if you see in this case, if you can see this particular circuit on screen, in the hydraulic section, on the right hand side, I'll zoom into this. If you see this, this entire section here, which has been zoomed into the hydraulic circuit, is a steering block. So in the industry, this entire thing with the valve, the metering device, and the two pressure devices here, this entire thing is one single steering block. So you can buy this entire steering block either from Bosch, Eaton, all of them manufacture these steering blocks. It is one manifold component, and around it you build the rest of the circuit. To this block, then you attach the pumping section here. On the top, you have these two cylinders mounted here. So this is a steering mechanism. Then to give it real loading conditions, we have the entire mechanism created here. Okay, this is the mechanism. And then we have the actual 3D for this entire system here. So I'll simulate this particular system here. So this system has proportional hydraulics. It has mechanism manager and 3D interface. And by using the steering wheel, you see I can operate the power steering here. This gives me a real simulation. Okay, so such type of industry-based applications, yes, you can have a combination. A lot of student projects, what they do is, we've had at least 20-30 such student projects. What these students typically do, they'll go to the industry. Okay, that's a good way of doing projects, especially during this lockdown time. And what you can do is, for example, this is a steering block which is manufactured by Eaton, the company. We can pick up a catalog. You can take the Eaton block like this. Students can recreate this block in Automation Studio. Okay, and then build the rest of the circuit around it. And then this will become a project which is study of an industrial component. So now this is a steering block. Similarly, you have hydraulic transmission systems which are industry manifold blocks. You have things like hitching valves. Those are again manifolds designed by industries. You also have this PVG valve category where you can build projects around it. So students can actually build industry oriented simulation projects by using such type of industry components here. So that is a good way of doing simulation projects, especially when students cannot access the labs in this COVID situation. So that was a system like that. Now let's come to okay, something very, very interesting is we have a defense organization in Pune by the name of Defense Research Establishment, R&D in Dighi in Pune. And this establishment has a fluid power group, FPG they call it. Okay. And one of their projects was the building a system for capturing an aircraft. Now what happens is either on a ship or on the runway, when the aircraft is in trouble and let's say it misses the landing tolerance level and it overshoots the runway, at the end of the runway there's a net, and that net is supposed to capture the entire aircraft, 60-ton aircraft at that particular speed. So that much of kg forces being applied. So this project was developed by R&D Dighi, a DRDO in Pune. And let me explain the system. It is very, very interesting. And being a defense project, everything has got a lot of backup systems. If you see in the pumping section, there are two pumping systems here. There's a left pumping section and there's a right pumping section. There's a double pump, two pump systems here. If these pumps fail, there's an electricity problem, there's a hand pump here, which you can use to pump this particular fluid. Another thing is, you'll see there are three accumulators here. These accumulators are designed in such a way that even if the electricity fails, let's say Pakistan goes and destroys our electricity grid, these accumulators will be charged enough that they can supply fluid to capture 3 aircraft which land one after the other. Okay, that was the design condition. Another condition was that these particular pistons which raise the particular net are initially on the ground at 0 degrees under the ground. And when this is raised, okay, they come to around 75 to 90 degree upstand position. And to these two pistons, there's a net which is attached. And this net has got a self weight of 900 kgs. So when the pistons are on the ground, the weight of the net is 0. But as the net is rising from 0 to 90 degrees also, there's an exponential type of a weight load of the net itself which acts on these pistons. So there are a lot of design conditions involved in a particular circuit like this. There are lots more which I can't, we don't have time right now, but there are a lot of design conditions in this particular circuit. So now we'll simulate this particular circuit. Okay. On the right hand side, there's a control panel. Automation Studio also has a HMI module where you can create these types of control panels. So I'll simulate this particular circuit here. And initially what we'll do is we'll switch on the pumps. First pump, second pump. The moment the accumulators are charged, you get a good amount of pressure reading. Then we'll raise the particular net. Okay. So I'll raise the particular net now. You can see the net has been raised. I'll just pause the simulation. The net has come up. And these are the pressure build-ups. Okay. If you see this particular section here, sorry. If you see the slight curve here, this is the weight of the net. So Automation Studio simulates this also very accurately. A small graph here which shows the weight of the net being taken into consideration. So the net has been raised. Okay. We'll start the simulation again. And now we want to bang a load of an aircraft ramming into the particular net. So for that, we've used a graph, and this graph will trigger a load onto the particular net at the center point. So I'll trigger this graph, and at one point this graph will shoot up and you'll see a buckling action on this particular mechanism here. You saw that? I'll do it again. So I've started the simulation. I start the motors. I raise the net. Okay. And the graph signal, and I want to see the effect on my net here. I'll trigger the graph. And you can see the effect on the entire mechanism here. Also, you can see the pressures built up in the system here. Okay. So such type of work happens in the industry in fluid power. We may not be aware because of the educational limitations we have. But such type of work also happens in the industry. This is a defense-based project. So that was the net project. Then let me show you something else. Another very interesting component, this is just for information. is something known as a priority valve, developed by a lot of companies. In this case, it is Eaton priority valve and power steering. Now, what happens in a priority valve is, see, this is a steering block. This entire thing is a steering block. You can buy this as a one-shot manifold block. And this is a priority valve here. Priority valve, again a component manufactured by Eaton. Now, what does a priority valve do? What the function of a priority valve is to prioritize the flow to one particular function of this particular system. So in this particular circuit, there are two systems here. One is the steering here at the top, and second is this piston which lifts up this particular tractor sort of a mechanism. Now the function is that while this tractor mechanism is coming up, where it is digging, picking up any load or anything, if I use the steering wheel, the flow to that mechanism should stop and the fluid should be diverted to the power steering. So any movement on the steering wheel should stop the flow to the piston and divert all the flow to the power steering unit. So that means give priority to the steering section. So if I simulate this particular circuit, and if you see, okay, that piston on the right is raising the particular load, but the moment I operate the power steering with my steering wheel, you can see the right hand side piston has stopped moving and the fluid is now prioritized to the steering unit here. The moment I stop steering, fluid goes to my right hand side piston again. So this is a function of a priority steering block. So a very, very practical industry application. Students can again create a project like this. It will be very interesting. So this is how the industry creates these circuits here. Okay, now let's move ahead. Let's come to PLCs now. Now, Automation Studio has three types of PLC libraries: Allen Bradley, Siemens, and ICE here. Okay. Now, people who are teaching PLCs, they'll realize the beauty of a simulation software like this. Okay. Now, before we come to the actual ladder diagram, and we're taking an example of a traffic signal, but before that, I want to point out certain areas. If you see, depending on what PLC logic you're following, there is a lot of difference in the ladder programming also. For example, both these components are T-on delay timers. If you see the timer on the top here, this is a Allen Bradley delay timer. The Allen Bradley delay timer works on a methodology where you have the input supply and you have a EN and a DN bit. Okay. So when the timer starts working, the EN bit comes high. When the timer stops, EN goes off and DN comes on. And these two bits are used for performing the control. Whereas in comparison to a Siemens T-on delay timer, this is very, very different. In the Siemens delay timer, we switch on the supply, the output goes high. Switch off the supply, the output goes low at the end of the timer. So there is a big difference in how you program by using which methodology. Typically, we have seen that the textbooks are following a sort of a Allen Bradley concept mostly. But in the industry, Siemens is very popular. So depending on what you're teaching, you have to be careful what the PLC logic is. It is not the same for every technology. Allen Bradley will be slightly different. Siemens is different. Mitsubishi is slightly different. So you have to be careful about this. Now in Automation Studio, in this traffic light signal, we have used an Allen Bradley delay timer here. So what we have done is we have built a traffic light from the HMI library here in Automation Studio, and we have used 3 delay timers here. So the first delay timer will switch on one set of lights, okay, opposite side of the pole, red and green. This will operate for 10 seconds. You can set the preset. After 10 seconds, the second timer will come on for 3 seconds, yellow light. After 3 seconds, the third timer for 10 seconds, and it will go back in a loop. Okay, that is the logic of this particular circuit here. So we'll simulate this particular circuit and I start it. So here you can see the ladder is directly controlling the traffic light. I'll just zoom into this. Okay, so in a software like Automation Studio, you can actually see where the signals are coming. It becomes very handy for troubleshooting. If there's a mistake, you can just stop simulation, go to a particular contact, delete it, reassign it to another input or output. Now, people teaching PLC programming, they'll understand the beauty of a software like this. In actual PLC programming, you'll have a PLC programming software. You'll create the register sets, analog, boolean, etc. Then you'll create a PLC logic. Then you'll take this, you'll bootstrap it to the real PLC. Then switch off this particular software. Then connect maybe a multimeter or LED lights, or connect to it to another system. If there's a problem in the logic, again come back, redo the whole thing again. Whereas in this case, you can immediately go and troubleshoot on the ladder itself. That is the beauty. Another thing is that we've seen most of the mechatronics practicals which we are teaching across the country revolve around these timers. Now this is a traffic light. If the same logic is for a washing machine, again there are 3 or 4 timers working in sequence. The logic is the same. Water coming in, stopping, motor rotating, water going out. Again 3 timers are used. If it is 3-phase motors, phase 1, phase 2, phase 3. If it is another similar logic, all of them are using timers in sequence like this. Okay, and even controlling hydraulic pneumatic circuits with PLCs, you can directly do that. I'll show you. Okay, now in this case, the control of an electro-pneumatic circuit is being done by a PLC here. So there are 2 sensors on the cylinder. On the right hand side, on the PLC input card, there are 2 sensor switches. On the output PLC card, there's a solenoid. There's a logic in the middle. If I simulate this now, okay. So a PLC is directly controlling an electro-pneumatic circuit here. Now, because of the beauty of the software, if I reduce the displacement of the pump, of the compressor, entire system slows down automatically. And so does the PLC. It responds accordingly to the pneumatic system. So such type of PLC practicals can be created. They could be hydraulic pneumatic based, or it could be without any hydraulics pneumatics. For example, the traffic light signal which we saw, it had no hydraulics, no pneumatics. It was just a 2D animation. So these are virtual systems which you can build. Let's say I take, let's say washing machine animation. It has no hydraulics, no pneumatics. It is just a PLC controlling a 2D animation. You can build virtual systems like this. Now here I start this. This logic is similar to the traffic light, 3 counters, timers working in sequence. 10 seconds water is coming in. Then the washing machine starts rotating. And then the water goes out. Okay. And while this is happening, you can also see the timer on the accumulator here. It is counting the timer. Okay. These are virtual machines. You can create a lot of different types of animations. Now coming to another area is we have little time. I'll not take more than 10 minutes now. There's a lot to show, but I have to skip a lot of things. There's a technology by the name of OPC. Now OPC is a concept which is widely used in even IoT today. I'm not switching to the PPT. I had a diagram of that because switching on and off is taking time. But what is OPC? OPC stands for Open Platform Communication. Around 20 years back, Microsoft defined the standard and it was known as OLE for process control. Okay. And what happened was different people were building different types of systems. For example, someone is making a PLC system, someone is making a software like MATLAB Simulink, someone is made what you say a data acquisition system, someone is made SCADA. A lot of the different things were evolving, and it became a problem that when you wanted to automate an entire plant, how do you communicate with each other? Because in a simple college and office, we know that you have Windows XP, you have Windows 10, this driver does not work with that does not work with this. And that is why something known as OPC was invented by Microsoft. And they said that I'll create this communication protocol, and every software and hardware vendor in the world should comply to this particular standard. So by using OPC, you can interface MATLAB Simulink to Automation Studio. Automation Studio you can interface to